Hello, everyone. My name is Maf Khayedi. Identify as an IT activist, and I graduated as a software engineer with a main focus in business intelligence. Currently, I'm a Microsoft Azure Data Scientist Associate. I'm also a Google Africa Developer Scholarship Mentor and AWS Educate X Ambassador. Today's topic will be about time series. We're gonna benchmark very famous deep learning algorithms applied on a data set that has a temporal aspect. And I'm gonna start sharing my screen with you. So, behold. So I guess you can see my LinkedIn page. You can react with me during this workshop by sending any text messages you want, or if you have you want further clarifications, you can text me after the workshop. And now we're going to start our workshop. So if you are following with me, just open Google Colab, which is a famous platform for data scientists and machine learning developers. You do not need to install anything. Everything will be provided for you on this online platform. And through this workshop, I will be explaining almost each source and line of code. So, but before we start, I'm going to give you an overview about what we're going to do exactly in this workshop. So artificial intelligence is a very trend subject, and it's an umbrella term for many technologies and many techniques that we use to solve real-life problems. Artificial intelligence is usually known for computer vision. Like one of the main and most trendy applications is autonomous vehicles. You can see autopilot with Tesla, you can see it with other companies. And one of the other fields of artificial intelligence is NLP, which is natural language processing. It gives us the ability to understand human language and to provide or actually generate text that seems like it's written by humans. Also for speech recognition and things like that. So these are the trendy topic in artificial intelligence. But our focus in here will be on time series. So time series does not have images, does not have videos, does not have text to analyze. So it's not one of the trendiest topics, but it's like my main focus. So my expertise in AI is a niche expertise is time series and sequences, and today's workshop is going to be about that. So what we're going to do, we're going to exploit very famous algorithms applied in computer vision and NLP. We're going to take those algorithms and we're going to apply them to a data that have a temporal aspect. And then algorithm by algorithm, we're going to build different models, and each model would be based on one or two of those algorithms, and then we're going to benchmark them. We're going to use a public data set on Kaggle, and that data set, of course, has a date, and we're going to use them to create our temporal deep learning models. So what we're going to do every time, we're going to track how good the algorithm is doing on our data set. We're going to record the score of the loss function and the score of the accuracy, and put them for to benchmark the rest of the models. So if you are following with me, I can refer you to my GitHub account. You can find the whole workshop. So it's easy for you to follow. So I think now you see in my GitHub. If somebody's not seeing it, just say that. And it will be time series and sequences with TensorFlow. And of course, we'll be using the great TensorFlow. The workshop is in here. So guys, you can refer to today's workshop from this link. So it will be my GitHub, MWFK, which is my GitHub username. And you're gonna find the time series sequence with TensorFlow. So today we're gonna focus on that. I know a lot of audience want to have some kind of support, and that support is makes it easy for them to follow the process and the logic. So if you have opened the GitHub, you can like open Google Colab from here, just click the button and you follow with me. Otherwise, you can create a Colab notebook from scratch. And that's basically what we're gonna do. We're gonna create it from scratch by copy pasting the code because it's too long, and we will try during 1 hour and a half to go through all the details. So it's really inconvenient to do real life coding. So we're gonna start by importing our libraries. And of course, since we are working with time series and sequences in the context of artificial neural networks, we're gonna refer to TensorFlow. PyTorch is great, but for me, I prefer TensorFlow. It has many features and it's easier to manipulate it. I know sometimes for PyTorch, you can like code, you can have the same source code, but it's like shorter and easier. But like if you go into production, if you try to track your models, TensorFlow is much better. So we're gonna start by importing TensorFlow and the other libraries that we're gonna use. And a good practice before like starting is to change the runtime type. So for the hardware accelerator, let's all choose GPU, which is graphical unit. It's much faster to train the data on a graphical card than to train data on CPU. But for inference, usually it's faster to use a CPU. So training data is usually faster with GPU. This is why we are choosing it. But then after you have the training model, it's better to use CPU for inference. But for today's workshop, we're gonna just train the model and see how good the model is performing. After that, I'm assuming you are seeing my screen. And if there is any issue, please let me know. By the way, you can ask questions. Do not wait till the end, even though by the end, there will be some time for interaction, but you can interact directly with me right now. So after importing TensorFlow, one of the best practices is to print the version, because versions can, for the new features, you're gonna find them in the most recent TensorFlow version, and it's easier to use. So the old version, sometimes you have some messy code and it does not look good. So in the new updates, it's like more clear and better. Before that, we need to connect. This will provide me like with a Docker environment that will help me easily install whatever I want, but usually it has the basic libraries. Then after that, we're gonna import CSV. So our data, which is hosted on Kaggle, and for us, we're gonna use another link provided by the great Lawrence Moroney, and we're gonna use NumPy for creating our arrays, and I'm gonna use Pandas because Pandas is great for manipulating data frame to put the details about each model I'm trying to train. And of course, for visualizations of the training, we're gonna use Matplotlib. You guys can use whatever you want. It's like, it depends on your convenience, but if you are in a production environment, it's preferably to use faster libraries like, for example, NumPy is much faster than Pandas. TensorFlow, if you work with TensorFlow tables, they are faster than NumPy, and it really depends on your context. In our workshop today, we will not focus on those aspects. In here, we're gonna focus about prototyping several models and compare them together. So we successfully imported our libraries. Now we're gonna move to the next step, which is the visualization. So I need a visualization function for my time series. I know even Pandas has its own visualization capabilities. I know a lot of people are working with Plotly. Personally, I'm working with Plotly, but I want the customized function for what I'm going to use during this workshop. So I'm going to paste this code, and this visualization function will enable me to put the time of my time series dataset and the series that I'm going to use, which is like the data that is not temporal. So I'm going to put the dates and the data that goes along with the date, and the format on when my series is going to start and end. If you are new to Colab, to execute any cell, you just press Shift Enter, and that's it. It's going to execute. And in here, you see it was like a couple of milliseconds. So it really puts 0 seconds, but it's actually a couple of milliseconds. After defining my visualization function, I'm going to download the dataset that I was talking about. But before downloading it, I'm going to go to the source, the original source, which is Kaggle. And we're going to discover together what this dataset is about before we start modeling our functions. So it's called sunspots, and sunspots are temporary phenomena on the sun's photosphere that appear as spots darker than the surrounding areas. There are regions of reduced surface temperature caused by concentration of magnetic field. I know this sounds a little bit out of like ordinary for you, but what we're gonna focus on is the last phrase. So sunspots usually appear in pairs of opposite magnetic polarity. Their parity varies according to approximately 11-year solar cycle. So in time series and sequences, we have things that are periodic. So for example, we have 4 seasons, like this is the periodicity of the time series. So in entire year, in the summer is going to be always hot, in September is going to be a little bit cold, and the winter is going to be always cold, and in the spring is going to be good weather. So this is periodic. Every year I have the same. And the cycles are similar to periods. So for me, this is not like 1 year cycle. It's not like the weather. It's like 3 months each. So every 3 months, I have a new period because I have 4 seasons. 4 by 3 is 12. It's an entire year. So my period is 3 months. In here, we are talking about cycles, and the cycle in my data is 11 years. So for that, I need, since the data is big, so in classical machine learning, if you are using, for example, a linear model, and my data is not linear, the model will not give me good results. So what most people do, they will just put an ensemble learning technique. That's good, but like what I have discovered during the last year working with not small data, I will not say this is like big data, but some ensemble learning models tend to overfit and does not give you, some of them give you a good result, but when you have a lot of data, it's preferably to use deep learning because it can go in depth in your data. It's not as easy as using ensemble learning techniques like XGBoost and CatBoost, but like it will enhance your model capabilities and it will benchmark better than, I'm not saying this are the rules. This is what I have interpreted after working 2 years as a machine learning developer. And this is why we are using deep learning. This is why we are using TensorFlow. And you will notice during this workshop is that you can have very bad models and you can have very good models. Does not mean you are using deep learning, you're going to have a great result. So in my 11 years, cycle will be big. It's not like working with 3 years each time, 3 months each time, 3 months for the different seasons. It's 11 years cycle. So that's big. And Before I start modeling, what comes to mind is the recurrent neural networks. The neural networks that have recurrent aspects, things that repeat themselves. So in NLP, the phrases I'm saying right now, they are based on the phrases I have already said. So to predict what I'm going to say, you need to know what I have said. This is a recurrent aspect. So when we are talking about periods and cycles and things that repeat themselves, we are referring to a family, a broad family of recurrent neural networks. So obviously we're gonna start with a simple RNN, which is a simple recurrent network, and then we will try to upgrade our game and try to make a feature extraction to enhance the capabilities of our models. So in here, we can go back to our Google Colab, and I'm assuming you are seeing this cell. So what we're going to do is like press Shift Enter, and boom, we have downloaded the data. The data will be located in a temporal folder, which is like TMP folder. You can guys come in here and discover what you have and what you do not have. This is like dummy data that you can use. And for what you have downloaded, it's in TMP, so temporary. You can find your data in here. It's a CSV format, so we need to import CSV. We've already done that, and we need to deal with that format. So now we're gonna, so the data is in the TMP folder. We're gonna import it from the TMP folder, and we're gonna put it inside the list, which will be a NumPy list. Why we do not use Python list? Simply because NumPy lists are much faster to calculate. NumPy is a wrapper around C programming language, which enable faster calculations. So we're gonna close this. We will not need it. By the way, if you need like a quick go-to code, you can like type whatever in here, like import CSV, for example, and it will give you dummy examples. So in here, I'm gonna paste the source code, and we will try to understand it together. So the dates, which is like the time, which is like the temporal aspect, which make my use case a time series and sequence use case, we're gonna put them in a Python list first, and we're gonna extract the CSV content into these two lists. So the first will have the time, and the second will have the value according to that time. We're gonna print them, and then we're gonna convert the data into NumPy format. After converting the data into NumPy format, we're gonna visualize what we have. So Shift Enter, everyone, and boom, this is my data. So what I have done in here, I took a quick look into what I have inside my CSV file, and it has the ID, the date, and the value. So now I know what I have inside the CSV file, and I can manipulate it correctly. So I have put the data inside Sunsplot lists, and we have put the timestamp in here. So the timestamp, we only made an incremental. It's like an ID 0, 1, 2, 3, 4, because my dates are in order. We do not skip days. We do not have different periodicity. We do not have like different ranges. It's the same. So it's okay for me to, from like 9/9/2020 or today's date 4/9/21, can just make an incremental list. So then I converted to a NumPy array. I convert the time to a NumPy array, and in my first array, I have like 3,235 elements. And for sure, I have the same number of elements for both NumPy lists, which are the series and time. And this is why I have for visualization. We see in here there is a periodicity in my visualization, which means we have things that repeat themselves. And based on that, we're gonna choose a specific type of algos to deal with that. But before that, I need to drink a little water. So guys, now we're gonna go to the next step after we have a brief interpretation of the visualization. By the way, this visualization was done by Matplotlib. It's very easy to use, but if you want to upgrade your game, use Plotly. Now we move to the next step, which will be splitting the data. If you use sklearn, you know the function that splits your data. But for us, we're gonna use like something very basic. So the split time will be 2,500 data points, which means it's 10 years worth of data. In my 10 years worth of data, I'm gonna split the data into train and validation. This is like the most basic machine learning thing. You always split your data, and in here I can like control it by myself. I do not need an external library to do something basic for me. And we're gonna use a technique is called windowed dataset, and windowed dataset is really known in dealing with time series and sequences. So if you have this much data, every time I'm gonna take a window of that data, and I'm gonna shift it to the right by 1 day, 2 days, 3 days, and each window will have 30 days. So I do not put all my data at once to be modeled by LLM, for example. No, we start by 30 days, then we shift by 1 day and 30 new days, 30 new days, 30 new days. And the source code for that is a little bit complex. So what I have done is I broke down all the steps, and you're gonna find it in green, which means like there are comments. And since I'm gonna benchmark my models, I created the pandas data frame, which is gonna have these features. So we're gonna have the model name, the number of layers, the unit per layer, the optimizer, and for the metric, previously I have said accuracy. For the metric, I'm gonna use mean absolute error, MIA. And for the loss, I'm gonna use Hubbard loss function. And some aspects need to be the same. So if we're gonna benchmark, we always need to use the same loss function, the same metric, and the same optimizer. You only change the layers, and of course, the algo you are using and the units per layer. But if you change the optimizer, you change like the learning rate, you change the momentum, you change the metric, your benchmarking will be invalid. So I'm gonna create a data frame, it's called benchmark, and I'm gonna execute that set. Now we're gonna together like do the hardest thing, which is like defining our windowed data set. So what I have done is like in here I put some brief comments that will help you understand it for now. But like in my GitHub repo, I have broke down all the aspects of this great function. So for you, you're gonna find it in here. So where are you? So it's in here. So we're gonna create a windowed dataset, and every line of code I have executed it separately in here. So 1 is the first line of code, 2 is the second line of code, 3 is the third line of code, and you can have all the explanation. So all of these explanations from 1 to 5 is just about these 7 lines of code. So I think they are 7, 3, 3, and 1, 1. They are 8. So you can follow the explanation over there. Meanwhile, as usual, you can just shoot me a message on LinkedIn, and I will be right now. So my window with dataset, I need the series and I need the window size. So we have defined the series already, and we have defined the window size already, and the batch size and the shuffle buffer. So for the series, we're gonna use TensorFlow expand dimension. So what is TensorFlow expand dimension? You can go back in here. So in here, you will see 1. You go back in here, and this is how I decrypt every line of code. A simple example, in here I have an array. When I put TensorFlow expand dimension, is going to be expanded like this. This is like the first pre-processing of the data before feeding it to our models. And the opposite function, so if I'm using expand dimension in here, I want to go back to the array format. I use squeeze function, which are TensorFlow way of manipulating series. So you can like entirely work with TensorFlow data structure instead of using other like formats like pandas and NumPy. After that, what we're gonna do is, so the DS will be my data set. After that, we're gonna take slices from this series, and we're gonna take each time 30 values plus 1, and we shifted 1 day ahead. So we're gonna start, for example, 1 September to 30 September, and in September there are 30 days. So from 1 September to 30 September, that's my window. Next time I process the data, it will be from 2 September to 1 October. The third will be from 3 September to 2 October. And this is how the window dataset technique works. And the code in here is not really classic because we are purely using TensorFlow to structure our data. It's not like using NumPy or Python based. And then we're gonna shuffle our data using the shuffle buffer, and we're gonna use the map function to map what I was talking about. Take my dataset and divide it in small groups of data, in small batches of data. So the map function, what it does, it makes, so instead of defining a new function, you can like use a nested function. So you will, if you want to apply a function on your data set without explicitly defining another function, you will put map. Lambda is an anonymous function. It only exists in this line of code. So lambda is going to have the list W, and from the list W, I'm going to have the last feature and the first element until the end. So this is what my map function is doing, and this is like the logic of the window with dataset. Because I have time and I have the data, and the value at that exact time is going to be column for time and the data. I'm going to take the second column of the data, and I'm going to start batching my data from the first element until the end. And then again, when you repeat the function from the beginning, you're going to have a shift toward the right by 1 day. So like I said, if you are still watching, that was like the hardest thing to do. And I'm going to open parentheses in here I'm going to talk about univariate time series and multivariate time series. So in univariate time series, I have one variable. So the other variable is the time, but the time is incremental. It's always one day, the other day, the next day. So I have only one variable, which is the value at each day. So this is the context of univariate time series use case. If I have two variables or more, that's a multivariate time series use case. And in here, I'm trying to predict the next day. So I have a single output each time, not a multi-output, just one output. So if I have various variables that I'm going to use and many outputs, it is going to be multivariate, multi-output time series analysis. But in my use case is univariate time series analysis. I hope that was clear. Well, otherwise, shoot a comment and we'll try to make things clear for you. Meanwhile, I'm gonna check Zoom, still working. And yeah, things look good. In here, I will try to execute the window dataset using Shift-Enter. And we're gonna move on to the forecast function. So in the forecast function, it will enable me to use data structure of TensorFlow. So each time I'm gonna give it the model and I'm gonna give it the series, but the series, like we have seen, it's in NumPy format. We're gonna change it to TensorFlow format. And each time we're gonna give it the window size. So of course, the window size for us, we already defined as 30, which means 30 days. And in here, there is a very interesting function, which is prefetch. So every time I'm gonna batch my data, I'm gonna use a batch, but I'm gonna prepare another batch before it. So I prefetch it. This makes my calculations faster. And each time I'm predicting one output at a time, so I only prefetch one batch at a time. And then I'm gonna forecast and return my findings. Shift-Enter and Shift-Enter to execute that. And then we move to our RNN model. So what I'm gonna do is copy paste the code I have prepared. It's too long to write right now. Let's see if there are messages about our workshop. Oh, okay. Hello, Sophia. So, hello. Now we're gonna try to understand line by line what my RNN functions do. So we're gonna fix this C to 41 is like a random number, so you have the same result as me. So there is randomness to the artificial neural networks. It's like the ensemble learning when you have decision trees, like splitting. It can be random, so we're going to have different results that are really close, but they are different. It's the same thing with TensorFlow, with artificial neural networks. So for us to have always a reproducible results that is the same for everyone, we fix it to 41. And now my train set is going to be not just a simple train set like you see in scikit-learn when you have train test split. I'm going to have a windowed data set. So my train set is windowed, which we have already explained. So this is the series, and we have made small batches of that series. So for the RNN model, it's a sequential model. So on TensorFlow, we have two types of models, either sequential models or API models. I forgot the name. And they behave in a different way. For us, since we are like trying to make a model based on a temporal aspect, is going to be sequential, and the most famous technique is RNN, which is a recurrent neural networks. From what I have in the past, I know in the future is going to replicate itself, not identically, like not 100% identically, but since I have a period, it's going to reproduce itself. So RNN can like remember short time batches. So if in 10 batches, RNN like can remember what happened in the recent past. So I emphasize on the recent past. But if my periods are large, we need to use a better algorithms. But we will now just try to execute it. It's going to take some time. So during the execution, we'll try to explain the rest. And this will be like the same thing we're going to do for all the models. So shift enter in here. And if it's wrong, this button will be red. We're gonna go back in here. So I know LinkedIn, there's like a follow button, but you can send an actual invite, so you can like connect directly and text me. And in here, what we're gonna input is the input shape. So with none, we can input different dimensions into our neural networks. And every time we're gonna use a lambda function to expand the dimension that we are using. So we have used this this expand dimension previously in the window with dataset. So we are expanding the dimension of the series, so it was flat, and then we expanded the dimensions. After expanding the dimensions and indicating that I can have various input shapes, I put the RNN, and I put 50 units. So what I need to record for this model is the model name, which is RNN, and then I need to record the number of units. And then I need to record the optimizer. So in here we have used stochastic gradient descent, which is a great optimizer, but you need to have a good learning rate and momentum. And for that, like to know the best parameters, it's better to use Keras Hypertuner. It's really a great tool to know. You can use it even to know the adequate number of layers and the adequate number of units and the adequate value to put for the learning rate and momentum. And you can even put it to guess, actually not to guess, but you can put it to get the best optimizer and the best loss function and the best metric for your problem and even the best epoch. It's going to take a lot of time for that. So that's why using the GPU on Colab is very beneficial. Even if you have a gaming computer, this will be like twice or 3 times better and faster than your gaming laptop. And in here, I'm talking from experience. I have a gaming laptop with a decent GPU, but like it's slower than like using Google Colab. In here, we have the output of our function and each epoch. So we have defined 150 epoch. And at each epoch, we are seeing that the loss function is either increasing. So if the loss function increases, that's bad. And we have the metric, which is mean absolute error. If the metric, the MAE is increasing, that's bad too. So we need to decrease the loss function and we need to decrease the metric in here. Because we are using MIE, it's better to have small value. A small value for the loss and the small value for the metric, in our case, is the best thing. And in here, we are seeing that the model is not learning in a good way. So sometimes it goes up and sometimes it goes down. We need to wait for it. Meanwhile, I can put like 50 epochs but in 50 epochs it's going to be faster, and it will not really learn a lot of things. So I remember the thing for the benchmark, you need to include the number of epochs. So in here, I should have put the number of epochs. But I think I will leave it for the other parameters. Because if you change the number of epochs for a model, you need to keep the same number in the next models. We still have a couple seconds to go, and before the training is finished, we're gonna prepare the code for the visualization. This is the code for the visualization. From the training, I'm gonna call history, which have all the data about my MIE. And we'll have the data of all my loss function. And I'm gonna zoom on the data to see a specific part of the training, and I'm gonna visualize it. So we need to wait until it hits 150, and then we're gonna make the visualization. If I'm going too fast, do not worry, because we're gonna repeat this 5 times. So it's gonna be RNN, LSTM, BLSTM, CNN, LSTM, and CNN, BLSTM. We'll repeat this 5 times, just try not to get bored. Well, it's gonna keep being interesting, because we're gonna see how models are performing on the same data set. It's almost done. 150, couple of seconds, and boom, enter. I'm gonna visualize my function, and here we go. So my model started learning, and I did not visualize the 100 first epochs because it's highly unstable, but I visualized the 50 last epochs. This is done by this code. And in here, we see our model is getting stable. Actually, it was stable in 105. So if I'm gonna repeat it, I'm gonna stop. Next time, I'm gonna stop at 120 epochs. That's enough for me. And in here, after the visualization, we are noticing that the MIE has decreased, which is good, and the loss function has decreased, and we need to store those very valuable information. We're gonna use the data frame that we have defined already. We're gonna define the name, which will be RNN. We have used 2 layers of RNN, and each layer have 50 units. Our optimizer was stochastic gradient descent, but you need to indicate the learning rate and momentum. And these are the 2 features that I'm gonna benchmark my models, which is my last MAE value and my last lost value. Just enter, and boom. My table is gonna get bigger each time. So now I'm gonna work with LSTM and try to decrease the MIE and the loss. So what I'm gonna do in here, I'm gonna copy paste. Obviously, you can see that this is a lot of source code, so it's more convenient to prepare the workshop beforehand, but I have a lot of other streaming videos where I do live coding. It's really hard. So I hit Shift Enter, and meanwhile, it's gonna take like 3 minutes. Meanwhile, I will explain the LSTM. So LSTM is the abbreviation of long short-term memory. So the problem with RNN, it does not remember, like RNN is good for remembering recent values, but if the values are really old, like we have a year ago, it does not really generalize well. So one of the RNN family derivatives is the LSTM. It's really great tool for time series and sequences modeling. It's really used in natural language processing. The downside of LSTM that it takes a lot of time. And after defining my model in here, we are seeing that the structure of my model is different. In here, I used another dense layer, but in the RNN, I did not use the layer. So when I define my benchmark, I need to say that it's a simple, that it's 2 layers of LSTM and 1 layer of one dense layer. Why I'm ignoring the last layer is just I'm going to have one output and it's the same for everything. That's why I did not even include the epoch. It's the same argument, but you can argue against that because I included SGD and it's the same for all. It's just like that's a really primordial parameter that I need to always include. Meanwhile, my model is training. I'm going to Socio platform on my second screen and check for the streaming on that platform is working correctly or not. Wait for it. So in here, meanwhile, the platform opens for me. In here, we are seeing that the last style is 77 and the MA is 78. And we are assuming that LSTM is better than RNN, but in here, actually, the LSTM is horrible. So a lot of people think, okay, I'm going to use LSTM because it's better than RNN, but it depends on your use case. Do not jump to conclusions before trying. And just follow the laws and the MA. They need to go down. And by this time, I know it's a horrible model. So not really familiar with this social platform. This is the first time I'm using it. So I'm trying to find between all the workshops, my workshop. And the great update about Colab, it was not like present a couple of months ago. When you finish executing, it puts an alert in here. It's showing on my second screen. And we're gonna do the same steps as we did with RNN. So we're gonna use the same code to visualize the result, and we're gonna use the same code that we have populated our data frame with. Obviously, this is a horrible model. If you find parallel, like between ME and those, the model is not good. This is underfitting. But we need to put it in our data frame to track the goodness of the model. So shift enter, and boom. The RNN is way better than LSTM. But now we will try to improve the LSTM with using something called bidirectional LSTM. So in bidirectional LSTM, it really takes much more time to compute. And the enhancement is having a state cell that runs from the beginning to the end of the model. So in LSTM, if you have a very long sequence, it's gonna forget. So it's long short-term memory, but if you have a very long sequences, it's gonna lose and decay over time. And sometimes I need to communicate the informations between the beginning and the end. If you are reading a poem, to understand the meaning of the poem, you need to read it from the top to the bottom, but sometimes you get lost. And for example, if you're reading Shakespeare, it has a lot of hidden meanings, and you need to go back and read what you have read like 5 or 10 minutes ago. This is not possible with LSTM. This is one of the derivatives of LSTM, which is bidirectional LSTM. It's capable to go back and see what happens in the past, so we try to generalize in the future. But do not make the same mistake as concluding that LSTM is better than RNN, so BLSTM, and some people call BiLSTM is better than LSTM. No, try both of them. try to understand your business, and then apply it. I'm gonna hit Shift Enter. I should have done that already, but like forget. It's gonna take more time, and the more the upcoming model is gonna take even more time to compute, and it's 150 epochs for all of them to keep the same benchmarking. So I'm gonna go back to the social platform, get familiarized with it. It will not show for you, it's on my second screen. But in here, we will try to understand a little bit more of the LSTM. So I have defined the LSTM layer with 32 hidden units, but I need to make my LSTM bidirectional. So what I'm adding here is the word layers.bidirectional. And notice I'm using Keras all the time. So Keras is a wrapper around the TensorFlow, and it makes our life much easier. But people argue that PyTorch is better because you have less, how to say it, abstractions. It has more abstractions, and it's like easier to remember and code. Sometimes TensorFlow and Keras, it will be dot something, dot something, dot something. And sometimes there is compatibility issues if you work with like TensorFlow 1.x. I think it starts at 1.5. That code will not run if your current code is in 2.x. There is other issues which are with how to build graphs. In PyTorch, it builds them dynamically, but like in TensorFlow, it's not dynamics. So a lot of companies are like, a lot of companies are shifting to PyTorch, but like it's bad for production and it does not have the number of features that like TensorFlow. And one of the best ones is TensorBoard and TensorHub. For TensorBoard, you can track all your models. And in TensorHub, you can use the transfer learning. So now I'm going to see how my model is behaving. So it starts with a loss of 24 and MAE is 25. So I'm assuming it's going to be better than RNN. And this is the epoch 61, and my model is not improving. This is a bad sign. So I'm assuming that RNN is going to be better. Do not only take in consideration the score and the MA, you need to take consideration the compute time. So if you are using cloud, you're gonna spend a lot of money. So if BLSTM is slightly better than RNN, then go use RNN because it's much faster and easier to implement. Meanwhile, we're gonna put the visualization of my training. But if you are using TensorBoard, there's a lot of, like last year, every time I use TensorBoard, there is a lot of issues. So just to be safe, I will be using a simple visualization, but like TensorBoard needs a little bit of maintenance. So I'm pasting the visualization, and then I will paste the creation of actually the appending of my benchmarking. I cannot like execute right now because it did not finish training. Still 60 epochs. This model has stopped improving a long time ago. I think it's going nowhere. In here, we are using a GPU. Like if you have put a CPU in here, it's gonna take forever. Like putting none is basically using a CPU. It will take forever. And for people that know how to use tensor processing units, which are TPUs, they are much, much faster than GPUs. But for this workshop, it's intermediate level. We are keeping it simple. Come on, come on, come on. And then the next two models will take even more time than this one. Sometimes it's a drag to wait. But if you are working with big data, you will wait for hours and sometimes a day or two, at least in my context. The largest model I trained, and since I do not work with multimedia, it's always tabular data. The longest was like 8 hours, which is a considerable amount of time given the AMLA. It was not computer vision and it was not NLP. I think it was on ensemble learning. Extreme random forests were known as extra trees. It's a really great ensemble learning. It's based on bagging, not boosting. Not all the ensemble learning techniques like cat boosting, XGBoost, they are based on boosting random forest and super random forest, which is like, it's called extreme and extra trees, and it has a lot of names. They are bagging techniques. So you need to consider your bias and variance, and based on those, you chose the adequate ensemble. Now, we go back to artificial neural networks and we visualize the result. And boom, it's bad. Comparing, it's not that bad, but like, it's bad comparing to RNN. But like, let's see our table. We populate with the new values. And the BLSTM is close to the RNN, but still I will use RNN because it's much faster. Now, what we're gonna do is we're gonna improve the LSTM, not the BLSTM. We're gonna improve the LSTM. And one of the best things to improve our models is to add layers, convolutional layers, because CNN is really great at extracting the feature. So if you extract the feature, you're gonna lose time using CNN, but then the other layers, it's much faster to compute them. So what you can do is like use CNN, export that part, and then each time you import what you have trained using convolutional neural networks. You do it one time, and then each time you load it and add new layers. That's the best practice. And why CNN is good? So when I was studying deep learning, I was so in the courses they tell you, okay, CNN can detect edges, CNN can detect those kind of things in side images, and I was like, if it can do that, it can detect temporal aspects if they are recurrent. I thought I was smart, but then everybody was doing it. So now we are doing it. And by the way, most of this content is from Coursera. It's from the preparation for the TensorFlow Developer Certificate. I really highly recommend it. And for you guys, if you want to prepare your Tensor certificate, just come to my GitHub. And for changes in this repo, the time series TensorFlow repo, you can just put a star. If you want to change things, you can like fork it. But if you want to get certified, just go to my repos. I have put all great notebooks. I'll put them for myself, but like you can use them. They are based on Coursera courses, but like they are significant explanations of the source code, and they are organized. So if there are other things like Keras Tuner, how to load and save models, that are really beneficial, and you can have you can find transfer learning too. So it's really, really rich. It's 15 notebooks. It will take you to master them around 6 months. But if you do it before that, it means that you do not really grasp all the details. So when you try to apply something by yourself, it's going to be a little different, unless you are only interested in one field. I know most NLP engineers, they only work on NLP, they love that. For computer vision, people are specialized on that. It's completely legitimate. For me, I found myself have only expertise in time series. So to prepare for the TensorFlow certificate, I spent a whole year like trying to browse and create different projects for me to understand them. By the time like I get a couple of freelance jobs, so I really learned a lot of things that I did not know before, and I put together, consolidated together all the things I have learned. And then here we noticed that running, so I had notification on my second screen, and here I noticed even adding CNN to LSTM is still faster than having two BLSTM layers. And it starts with a loss of 16, an MAE of 17. So it was 77 with only LSTM, but this is when adding CNN is 16. This is really, really huge difference. This is going from underfitting to fitting. And we see that it's stable, it's always 16, 17. And in here, we try to add those values to our data frame. But before adding those values, we need to print what we have trained. And we have something really beautiful. The MAE is going down, but sometimes it's going up. Maybe we consider training the model for more epochs. But for me, I'm assuming if I'm going to do it again, it's going to be 110 epochs. That's it. But like you can train it for 200 epochs just to be sure about this spikes in the data. Now we're going to put the new data to the data frame and visualize all the models. And here we go. CNN and LSTM is way better than RNN, and it's really fast. So for me, for now, I will use CNN layer on top of LSTM layer. But before doing that, how about we add a CNN layer on top of BLSTM layers? That's gonna take a while to finish, but I think it's worth it. We will try to have a smaller MAE and a smaller loss. And for that, I'm gonna copy paste the code you have prepared previously, shift enter. And in my code in here, it is not just like BLSTM, I have also LSTM layers. So you need to experiment with the layers, you need to experiment with hidden units, and that takes days and days and sometimes weeks and weeks. And tabular data is usually much faster computing than multimedia data. And for that, I recommend Crest Tuner. There are other libraries. And I recommend working on GCP, even though I'm certified in Microsoft Azure, but like GCP is cheaper. And it's easier to use, and it has a lot of resources to learn, like Quick Labs. You just pay $50 for a whole month, and you can like try all the labs you want, and you will be an expert on that in like 1 or 2 years. But for Azure, all the training you need to pay for. So I have 2 layers of BLSTM, which have 32 units, and I have 2 layers out of LSTM, and it has 64 units and 1 dense layer, 2 dense layers, one is 30 and the other is 10. And the output is 1 output, which is in the last dense layer. And we keep the same number of epochs, the same optimizer, the same loss, the same metric, and we pray that we have a better result. So the score to beat is 1716. So in here we started by 50. I'm assuming that was not a good start, but then it's drastically dropping and keep on dropping. So I'm assuming it's gonna be, so after 30 epochs, after 30 epochs, I'm already really close to my best model. So how did you put that code together? You actually put layers and you start to experiment, or you use Curious Tuner and you put all the layers and see which knot is putting good effort and give you a good score. And this is like, I don't know why I'm smiling, but I guess I'm a geek. So I like these kind of things. Let's go to LinkedIn. Hello, Theophilus. I'm hoping I'm spelling your name right. Theophilus Mathema. Hopefully that I'm saying it right. So I'm following the workshop. Please, yeah, of course. So this is my GitHub. So today's workshop is in TensorFlow sequences. And today's workshop is in this file. I always update these files so you can start it, get it, and send. There we go. By the way, I have a lot of free projects on my GitHub. You can check them. I work as a data scientist and I develop machine learning models. So I have a full-time schedule, but in my downtime, I try to create small projects. Of course, in my full-time job, I have much more interesting things to talk about and say, well, it's confidential. I wish I can put them on my GitHub. So where are we? It's epoch 120. And boom, we have a loss of 14 and MAE of 15, and we are beating the CNN LSTM. Ladies and gentlemen, putting in BLSTM, 2 BLSTM layers, under them 2 LSTM layers, is giving me putting a convolutional neural networks to extract the data under them BLSTM that can memorize and generalize really huge sequences. Under that, we put LSTM that has a long short-term memories, which is better than LNN, and then condensing the result to 30 units dense layer, then 10 units dense layer is giving me amazing results after 120 epochs. Theophilus. Okay, thank you very much. You are welcome. I really love when I type, like give you suggestions, it's much faster. Your profile, so let's keep it in here. And boom, it's finished. So the loss is 13 and the MA is 15. Congratulations, guys. You sit through one of, I would not like to say one of the best workshops, but I'm too excited. Everything has worked great. And now we're going to visualize what happens inside those neural networks. Going to paste that code and boom. This looks amazing because the MA is continuously dropping, but the loss function is continuously dropping. So this is like a slight spike, but like we can train for 200 epochs and verify. But this is, guys, the best result we had. It's not by chance because of course I already prepared this beforehand. And what we're gonna do is we're gonna put these new values inside our data frame, and we will finally visualize all the results. So I'm gonna put benchmark, I'm gonna create text. No, it's not a list. Show it in big size. Benchmark all models. Shift enter. Enter in here, and in here we're gonna print benchmark. So let's forget about this because I have shift enter twice. Ladies and gentlemen, the best model that we have created during this 80 minutes is CNN BLSTM model. It's actually CNN BLSTM LSTM model. It gives me the best MAE score and the best Habermas score, giving the same parameters for the optimizer, the epoch. It's a little bit complex model, but surely it gives us the best result. So in here, just I have press shift enter twice, so that's why it's twice. We can like shift enter again. It's gonna appear 3 times, so no biggie. So we have complex models like LSTM, CNN LSTM, but in RNN it gives me an average good model. So that's my benchmarking baseline. My baseline was the RNN. I was trying to go down, but it went up with LSTM, it went down with BLSTM. It was great with CNN LSTM, even though LSTM by itself it was horrible. But then we found the silver lining. Then we found our, I will not call it holy grail, but by now you know I'm a geek. So my best model is CNN BLSTM. This is what I recommend for Sunsplot. Surprisingly, it works on good on other data sets that are univariant. But guys, when you create models, try to have a plethora of models, but logically. Since we are dealing with cycles, periodicity, oh my God, some words just like does not come up right. Try to use different models to know where you are going, and then try to copy paste from here. For example, you wanna, for example, actually I cannot talk about that example, it's confidential. Most of my work is confidential, but like if one layer for RNN did something good, and you can add it to remedy something bad done by another layer. So it can be complementary. And for the CNN, it's not always, it's not like it's not a rule to always put it on the top for features extraction. Sometimes with CNN with a big kernel, it will make you lose data. Actually, if you do not have a lot of data, CNN will be horrible. There are no rigid rules. This is the beauty of it. You can experiment by yourself, and you can write your research paper and publish them. Hopefully one day I will have the time to do that. And if you are listening to me and you are in Tunisia, if you are good at writing, I can hire you to help me with my freelance jobs. I really need the help of, if you are a student, that's okay. If you are starting your career, that's okay. For me, I will pay focus to your tech capabilities. It's okay if you are not the best communicator. I know that in tech community, there are a lot of people that are a little bit self-restrained, but we will try to work that out. Overall, I think we have covered a lot of ground, and this is like most things that you will encounter in use cases involving time series and sequences. Last but not the least, if you have followed me using Colab, you can just save your work by save a copy in GitHub. If you have like a repo for a lot of notebooks, or just save it in GitHub Gist. Or if you are a big fan of Google Drive, I don't recommend that you save them in Google Drive. Just put them in GitHub to showcase your work. Or if you want to use PyCharm, I really recommend PyCharm if you are working on your desktop. It's good for packaging your softwares, especially if they are .py. You can download them as a .py and like use PyCharm to package your software. Other than that, if you have questions, please feel free to ask them. It will be like, I guess, 1 minute. I will put my LinkedIn in case you want to send text. We will wait for like a couple of seconds or a minute. Otherwise, that's it for today's workshop. I hope you liked it. and please feel free to communicate back with me. I know it's going to be uploaded, I think, on YouTube. If you find the video afterwards and you want to discuss things furthermore, or you find things that were not 100% accurate, you can always communicate back with me and I will try to answer them. Just one thing I don't do, I do not correct source codes. It's really good if I correct all mine, but I will try to put you in the right direction if I had already set up GitHub with the work that you need. I will freely give it to you. Just one thing, I usually do not correct other people's source codes, but other than that, feel free to communicate. That's like the best thing about learning. This is what we have done today. It's not that easy. It's not that short. It's not that long, but surely it's a good and really beneficial if you are working with tabular data. In general, not time series and sequences. General with tabular data, that's really great. If you sit through the whole workshop, congratulations. I'm really proud of you. And other than that, thank you so much for being with me today, and happy coding.
My name is Walid Krishen, and this is the workshop on Introduction to Recommender Systems. So this workshop will be about 3 hours. We'll be spending them together learning about recommender systems. I'll quickly introduce myself and then we can get started. And as a reminder, before we get started, if you have questions, please ask them on Socio. There's a Q&A tab. You can ask your questions there. And we'll be taking some breaks during this workshop, and I'll monitor the chat during the breaks and answer questions if we have time. So I'm Walid. I've been working at Google Research for about 5 years now. I work in a team called Laser, and we work on a number of topics, including recommender systems and other things like optimization methods and natural language understanding. So as a quick overview, this workshop will be split into 2 parts. The first part will be a lecture where we will be going over sort of basics of recommender systems, but also doing a deep dive onto some methods, some specific methods, things like matrix factorization, and also neural network-based methods. And then there will be a second part, which I hope will be the fun part, where there's a collab exercise or project that we will go over together, where you can actually train a fully functioning recommender system. It will be a simple system, but it will be a movie recommendation system that you can sort of poke and experiment with. All right, so with that said, let's get started. So we will start with sort of defining what a recommender system is and why we care about them. And here I took a few examples that hopefully many of you will be familiar with. So if you go to the YouTube homepage, for example, you may see something like this, where you'll see some video thumbnails organized in what's called shelves. And some of these videos might be, for example, related to what's currently trending in my area. And some of them might also be related to previous videos that I've seen, to what the system thinks is relevant to me, or topics that are of interest to me. And here maybe you might see a couple of machine learning related videos, some things from the news related to COVID-19, some new music videos of artists I previously listened to, and things like that. So any signal from my previous activity that can be useful can generate recommendations for me. Now, another type of recommendation still on YouTube, but that is slightly different, is if I'm watching a specific video, for example, here it looks like some math video, then if you look on the side, you will see a number of recommendations, suggestions of what to watch after this video. And here the recommendations will be related to the video content itself. So maybe I have a number of interests, but if right now I'm looking at math videos, then the system may infer that I am sort of more in the mood to watch math videos. Okay, so it'll be good to keep in mind these 2 types of recommendations. Here's another domain. So we looked at recommendations in the video domain, but here, for example, if I go to my Amazon homepage, then you may see somewhere on the page some recommendations like this. So it looks like recommendations for magazines or books, and also recommendations from board games. I do play a lot of board games, so this is quite relevant to me. And as you can imagine, there are many other applications similar to this. Retail is one, like Amazon, so recommend product to buy. This is applicable to media, as we said, so recommending videos or news articles. You can imagine recommendations in travel, for advertising, and so on. So the applications are many, but why do we need recommendations? So in the YouTube example, you might argue that, after all, the user can just search for the content. There is a search functionality in YouTube. But usually, in many of these examples, the corpus size is so large that search alone might not be an efficient way to find the content that the user is looking for. And sometimes it's also possible that the user would like something, but they don't know about that topic yet. And we'll come to some examples and how a recommender system might be able to infer that. So one motivation or one reason why we care about recommendations is for content discovery. And the other one is to keep user engagement. So if you only rely on search, then maybe finding the content would be difficult, or the user will not find new content, and then they will just leave the service. Now, before we dive a little deeper into the different components of recommender system, here's a sort of system overview. A typical recommender system will be split in different stages. The first stage is usually called candidate generation, where the task is basically to narrow down from the entire corpus. So think of all the videos on YouTube. You want to narrow this down to a set of candidates that are relevant to the user and to the current context. So any information we have about the user in this context, we try to use that to extract a number of candidates. So these should be relevant to the context, but not necessarily the videos that we will show. And this first stage, because of the potentially very large corpus size. So in YouTube, for instance, there are billions of publicly listed videos. So this first stage has to be very fast and efficient. So you don't want a very complicated and expensive model to run on, let's say, 1 billion items. Okay. Then once we have generated these candidates, the second stage is usually called the ranking stage, where you take those candidates and look at them more precisely. So you can, for example, look at more features. You can use a more complicated model to rank these candidates, and then you will take the top 10 or 100, let's say, and then show them to the user. Okay, and I will talk about both stages in more details. So let me also introduce a little bit of terminology. I'll be using the term user to refer to any information we have about the user in the context. So this can be, features about the user herself, or also features about the context, like you can imagine using the time of day. So maybe the user's interests depend on the time of day or the day of the week. Maybe there's even text features. So let's say, the search problem itself, you can think of it as a recommendation problem where the user issues a text query. And then from that text query, you want to find the items that are most relevant to that user and to that query. So on one side, there's the user. On the other side, there's the item, which is the entity to be recommended. So in the YouTube example, this would be the YouTube video. So this is the video itself. So think of it as an ID representing the video, but also any other features we have about the video. So let me now talk about this first stage, candidate generation. The goal, again, is given a user and a context, we want to find a set of relevant candidates from this entire corpus. And the example to keep in mind is let's say 100 relevant videos from a corpus of 100 million or maybe 1 billion. So the way to do this, our general strategy, will be to learn what's called embeddings for both users and items. Okay, and so this notion of embedding, you might have encountered it in other applications. An embedding is just a term that means that we will use a vector representation for these entities. So a vector representation for the user and a vector representation for an item. So just, in other words, in simpler terms, it's just a list of numbers that the model will use to represent the user and the item. And then what do we do with these vectors? So at retrieval time, when the user comes to your website, so given the user embedding and given the embeddings for all of the candidates, we're going to return the best candidates. And this is done according to some similarity measure. So let me give an example. Let's say, this is a toy example where we have one user represented by this black arrow, this black vector. And then we have 5 candidates with the different colors. And then one possible similarity measure is the dot product. In other words, the score of each item will be the dot product between the user's embedding and the embedding of that item. Okay. And remember, the dot product, you can think of it as the projection of one vector onto the other, scaled by the norms of the two vectors. And so in this case, if I project this yellow item, so I project all of the items on the user embedding, and then I order them by the magnitude of the projection. Okay, so according to this measure, item 3 will have the largest magnitude, so will be the most relevant, and then it's followed by item 2, and then 1, and so on. Okay? And there are different similarity measures. Another one that's frequently used is the cosine. So here, we look at the cosine of the angle between the two vectors. And remember, the cosine is a decreasing function for small angles. So cosine of 0 is 1, and then it decreases. So in this case, a smaller angle means more relevant. So according to this metric, item 4 will be the most relevant, followed by 5, and then 3, and then 2, and so on. Okay. So later on, during the collab, we will see actually the effect of the different similarity measures. But this gives you an overview of the general strategy. So first, learn vector representations of these entities, and then whatever similarity measure you use tells you how relevant each item is to each user. Okay, so as a reminder, remember that the dot product between the two vectors is the cosine between the two vectors multiplied by the norms of the two vectors. So you'll see actually that these two similarity measures are related to each other. So the cosine is nothing other than the dot product of the normalized vectors, so if the norms are 1. Okay, so now I'm going to dive a little deeper and look at how we can actually learn embeddings for these for the users and the items. Okay, and so traditionally there have been two types of recommender systems. So one called content-based filtering and the other called collaborative filtering. So I will quickly go over the two, even though this is more, I would say, for historic reasons. So nowadays, most recommender systems tend to mix a little bit of both. So we'll have some content filtering and some collaborative filtering. But let's look at the two simple cases. So when we have content filtering, it means that we're going to train the recommender system mostly on the features of the items. Okay. So imagine we want to train a movie recommender system, and we're going to use two main features, so two axes. Okay. The first axis is going to be, is this movie a blockbuster or an art house, sort of an independent movie? And the second axis is this movie for children or for adults? Okay, so think of it as, is the plot sort of simple for children or complex for adults? And so once we decided on which feature to use, what you can do is place your or assign feature values to each of the movies in your corpus. Okay, so here, let's say, I took a few examples, but your corpus size, of course, might be a lot larger. So here we have some examples of blockbuster movies like Star Wars, Inception, Harry Potter, and so on, and then we have other examples of independent movies. So one thing to keep in mind is, if I place a movie somewhere on this plane, I'm assigning a vector of two numbers to this movie. Okay, so I will assign it a value for the first feature. So is it a blockbuster or art house? And another value for the second feature. So think of these to simplify as values between -1 and 1. So on the first axis, -1 means it's blockbuster and 1 means it's art house. So once I've done this for all of the movies, so I do this for other movies. Here I'm not showing the pictures, but let's imagine there are many. And then I have to do the same thing for the user as well. So remember, we need to learn a vector representation both for the user and for the item to be able to compute the similarity between the two. And you might ask, how can we compute the same thing for users? So one simple way to do this is you can just look at the previous items that the user consumed. So for example, if this user happened to watch, this particular movie, then I can assign the same vector to the same user. Now, of course, if the user watched several movies, then I might come up with one way to combine all of the embeddings or the vectors for those movies into a single vector for the user. For example, you might take the average or some other way to aggregate this. Okay, so now we ended up with a vector representation for each of the items and for the user. And then, as we said, during inference time, so when I want to generate recommendations for this particular user, I can look in this embedding space or in this vector space, what are the movies that have the closest embeddings according to my similarity measure. So if we're looking at dot product, for instance, this might be the most relevant candidates. Here's an example again of what would happen. Let's say now the user watched 3 movies instead of just 1. Then we will assign the user some embedding around this area, maybe the average of the 3 embeddings. So to summarize content-based filtering, some of the advantages is that the similarity is based on item features. So because of that, you basically don't need any data about other users. So you can generate recommendations in isolation for each user. So as long as you have, let's say, some sample of what the user is interested in, then you can understand the interests of that user. And because of that, you can also capture very niche interests. So if the user is interested in a very specific topic, as long as you have seen activity like that from the past, then you can generate recommendations on the same topic. Now, of course, on the flip side, because this is relying so much on item features, you need some domain knowledge to be able to train such a model because you need the right features, right? And also your recommendations will only be as good as the features. So if the features are not good enough to capture a fine enough representation of the user interests, then you'll not be able to generate good recommendations. Now this brings us to the other type of recommender systems, which is called collaborative filtering. So here the main idea is that instead of looking just at item features, we want to learn similarity at the same time between users and items. So let me give an example. So just to show you the types of behavior that we would like to capture. Let's say the system learns that user A and user B are similar in the sense that they watch similar movies. Okay, so we want that we know that their interests tend to be similar, and then user B liked the movie Inception, and then the system can infer that even though user A maybe has never seen similar movies, so has never seen movies from the same director or from the same genre, then they may probably be interested in this movie because their tastes are so similar to the other users. Okay, and this is what we sometimes call serendipitous recommendations. So from the perspective of user A, when they get this recommendation, maybe they never heard of this movie before, or of this topic, let's say, and then they watch that movie and they discover that it's actually very aligned with their taste. So it's in some sense discovering a new topic or a new movie. And this, as you can imagine, this sort of behavior is not really possible or is not easy to accomplish with just based on the item features, only with content filtering. It's much easier with collaborative filtering. Let's look at an example for collaborative filtering. One way to think of the problem is this matrix where one row of the matrix represents a user and one column of the matrix represents an item, or in this case, a movie. Okay, and then the values inside the matrix are a measure of interest. So this can be, there are different ways of obtaining these values. You can get what's called explicit feedback. So for example, the user after watching the movie might give a rating. So a number of stars between 1 and 5, let's say. And many services, used to do this or still do this. For example, Netflix at the beginning used to, ask you to give a star rating. I think now it's a binary thing. It's either thumbs up or thumbs down. So you may get explicit feedback like this. Or you might have implicit feedback, where implicit means that, for example, if the user watched a movie, then they are more likely to like that movie than not to like it. Okay, so you can infer from the user's activity what things, what entries in this matrix should be ones and what entries should be zeros. And then you can do something in between. Like, for example, if the user started watching a movie and stopped in the middle of it, then maybe they are less likely to like that movie. Or if, for instance, they watch a movie several times, then there's even a stronger signal that they like that movie. Okay, but this is something that the user did not explicitly say, so did not explicitly give a number rating, but rather we infer implicitly from the user activity. So now let's say, to simplify, let's take this example. So it's a binary example where we have some entries that are ones and everything else is zero. And of course, keep in mind that this matrix is very sparse. So it has very few ones compared to the entire size of the matrix, because any user will only watch a small fraction of the available corpus. And so this should be clear for movies, but it's even more clear for something like YouTube. So YouTube, as I said, there are billions of publicly listed YouTube videos. Any user will only interact with a tiny fraction of this entire corpus. Okay, so now given this matrix, we're going to try to do, I'm going to put this matrix on the side up here, and we will try to learn item and user representation in a collaborative filtering way. So let's start again from the example we had before, right? Let's say hypothetically that I'm going to assign embeddings or vectors for each item as before, so based on features. We will see later how to learn these automatically. So let's start from this configuration. And now the question is, I'm going to look at each user at a time and then decide what embedding to assign to that user. Okay. Here, if I look at this user, I'm also highlighting the row corresponding to this user in the matrix. Okay, so this user watched these 3 movies. What I can try to do is assign an embedding to this user such that the dot product between each user and each item is close to 1 if that item is watched by the user, and it's close to 0 or -1, let's say, if the user didn't watch the item. Okay, so this is a problem that I can formulate mathematically. So before, remember, in content filtering, we did something similar where we just said, okay, let's assign, let's say, the average of the embeddings. But here we want something a little bit more principled, where we say that since our ultimate goal is to have the similarity between the user items and the user embedding and the item embedding. So let's actually try to assign, in a sense, the optimal embedding for the user that is as close as possible to all of the items that this user watched and as far as possible from all of the items the user didn't watch. And this is something that we can formulate as an optimization problem and solve or learn automatically. And we'll see this in a few slides. So let's say the solution for this user is this vector. And then we do the same thing for the next user and the next user and so on. Okay. So we apply the same procedure to all of the users. And we end up with this configuration. But now the main observation is that we can actually do the same thing for the items. But before we do this for the items, let me show another picture. So another way to look at what we just achieved. So given this configuration, another way to look at it is that we are assigning a 2-dimensional vector, so 2 numbers, for each of the users and each of the items. Okay, so here I'm sort of displaying each of the vectors next to the corresponding user and next to the corresponding item. And what we want, again, is that if I look at any entry in this matrix, then the dot product of the corresponding vector on the row side and on the column side should be close to 1 if there's a 1 in the observation matrix, and close to 0 if there's a 0. Okay, so now we can also do the same thing on the column side. So now, given the current configuration, I can look at one item at a time and also try to assign that item the optimal embedding that would also make the dot products close to 1 when there's a 1 and close to 0 when there's a 0. So now if I look at the first movie, then this movie was watched by these two users, and then I can run this optimization problem for this movie as well. And then maybe the solution will be, slightly different. So it will be closer to these two users. Then I do the same thing for the next movie. I update its embedding, and then I do this for all of the movies. Okay. And what I just described here is actually one method. So one method called alternating these squares, where we do exactly this. So we alternate between updating the user embeddings and updating the movie embeddings. So now where the magic happens is that in this example, in the story example, I actually started with manually assigning vectors for the movies. But what you can do is you can randomly initialize all of the embeddings of the items and the users, and then apply this procedure. And from this initial random configuration, the model will actually eventually learn embeddings for all of the users and items such that the dot products make sense. So such that we reconstruct this the input matrix. So we don't actually need features for any of the items. Okay. So the next question is, how can we actually automatically learn the embeddings? I showed you a toy example, but now let's formalize the problem. And there are two techniques that we will look at in more details. One is matrix factorization, and the other one is neural network based. So sometimes they're called neural embedding models. So first, matrix factorization. Matrix factorization is actually, in some sense, the simplest form of collaborative filtering. And the goal, again, is to have this ground truth matrix, or this observation matrix of interactions between users and items. And you want to approximate this by the product of two smaller matrices. So one matrix for the user embeddings and one matrix for the item embeddings. Okay. So I'll let you think about this for a minute or so. And because what we achieved by computing, by learning these embeddings for the users and the items is exactly this. So we want the original matrix to be close to the matrix product between, let's call them U and B transpose. Why? Because we want the dot product of any user embedding and item embedding to be close to the original matrix. But if we do this dot product between all of the pairs, then what I'm actually computing is the matrix product. Okay, so think about this for a few seconds. So hopefully you've convinced yourself that we are, after all, doing matrix multiplication between these two matrices. So the goal is exactly this. So we want the ground truth matrix A to be close to the product, the matrix product between U and V transpose. And the question is how do we learn U and V? So A is the training data, so it's the input data, it's what we have observed, and U and V are free variables. So this is what the model will learn. So one way to do this is we can just define a loss function that measures the discrepancy or the difference between the ground truth and the reconstruction of the model, which is this product, U times V transpose. And once we define the loss function, then we can minimize it. So there are many methods to do this. For example, one general purpose method is gradient descent or stochastic gradient descent. So let's go through some attempts of defining a loss function for this problem. Okay, so the first one is we might just say, okay, among this matrix, this ground truth matrix, we will actually only care about the observations. So whenever we observe that the user watched a movie, we want the prediction of the model to be close to that, to be close to 1. Okay, so this is our first loss. It's the sum over all indices I and j in the observations of Aij. Aij is the ground truth, minus the dot product between ui and vj squared. Okay, so this is a least squares loss. And the dot product, remember, is the prediction of the model. So this is our similarity measure, or what the model predicts for that entry in the matrix. So now if you look at this loss function, you might see a potential problem, especially in this example here. So in this binary example where all of the observations in the matrix are actually ones. So what might be the problem? Now think of this learning, this learning task. We're just saying that for any pair, I and j, all of the training examples, we actually need to predict one. Okay, so all of the terms in this loss, aij is equal to 1. As a learning task, this is actually a very easy task. The model just needs to predict 1 for any pair I show it, right? And this is, in fact, also easy to achieve. So I could, for instance, just assign the same vector, the same embedding for all of the users and all of the items. And if that embedding has norm 1, then the dot product of the embedding with itself will always be equal to 1. Okay, so with this trivial model, the model is actually making 0 training error. But of course, this will not have any generalization ability, right? So if I show it another pair, it's always going to predict 1, whether that's relevant or not. So we would still like the model to learn to distinguish between things that are in the training data and things that are outside the training data. And this is what we will try to fix with the next versions of the loss. So now the next thing you might try is, let's say, okay, I can put a prior that if something is not in the observation matrix, then I would like it to be 0. Okay, so 0 or any other prior. So it doesn't have to be 0. Maybe it's something that's maybe slightly higher, but still not 1. Okay, some other value. And then we still minimize the least squares loss. Now, in this problem, you might also observe another issue. So before I talk about the issue, one nice thing about this problem is we can actually solve it very efficiently. So you might be familiar with the SVD, or singular value decomposition of the matrix. Here, because we're minimizing the squared norm between A and the product of U and V transpose, the solution is exactly given by the truncated SVD of the matrix. So we only take, for example, if U and V matrices have rank K, then we only take the K top singular values and singular vectors of the A matrix. And this is something that can be computed very fast. Now, on the other hand, this loss function turns out to be not very well suited to the problem either. Because remember, we argued that this matrix is very sparse. So it has very few ones and is mostly zeros. So if you want to compute the SVD of this matrix, so you'll quickly realize that the reconstruction of the matrix is going to be extremely close to 0 because the original matrix is dominated by zeros. So in a sense, you want to assign weights to the observed part matrix and the unobserved part of the matrix so that the two have a balanced contribution to the loss function. And this is what we're going to do next. So basically, we split the loss into 2 parts. One where we sum over this part highlighted in blue, which are the observations, and everything else is highlighted in orange, which is the unobserved. And there we're going to fill in some prior. So here I'm using 0. Okay, and then we weight the second part, let's say, by some coefficient alpha. So this alpha here, think of it as a hyperparameter, and in general, it's going to be very small because the second sum has much more terms than the first sum. So alpha can be something like the sparsity of the matrix, right? So the fraction of ones in the matrix. Okay, so now that we have designed this loss function, what you can do next is optimize it. So let me show one more interpretation of what we just talked about. So this ability, or this the fact that we need to take into account the unobserved part of the matrix, not just learn all the observed part. because again, this is a toy example, right? It's a binary matrix, and you might be in a situation where the observations are more granular. So instead of just having ones, you might have some real number or some rating, let's say between 1 and 5, measuring the so the relevance of each item to the user. But even in those situations, you might end up with a bad behavior if you don't take into account the unobserved part of the matrix. And here I will try to show another example or another interpretation of this phenomenon. So suppose that your data is clustered, okay? And here on this figure, each color represents one cluster. And the users are represented by circles and the items are represented by squares. And in reality, of course, it will never be as clear cut as this picture here. But it's true that in general, the behavior is clustered. So think in YouTube, for instance, the most basic form of clustering is by languages or locales. So you might have, let's say, English-speaking users that mostly watch English videos, French-speaking users that mostly watch French videos. Of course, you will have, users watching videos in other languages. So you might still have interactions between these clusters, but the user behavior is mostly clustered. And then within each cluster, you will also have subclusters by topics and so on. Okay, so but let's assume that they are just clustered like this. And whenever there's an edge between two nodes in this graph, means that there is an interaction. Okay, so it means that this user consumed this item. Now, if you only train on this data, if we only train on the observed part of the matrix, it means that we are only showing the model the existing edges in this graph. Okay, so the model might learn very well how to place nodes within each cluster relative to each other. So it knows that within this cluster, let's say these users are similar to each other, these items are similar to each other, but it has no idea how to place the different clusters compared to each other. Okay, but because we showed no training examples of interactions between two different clusters. And what might end up happening is that by chance, it's just going to place the vectors or the embeddings of different clusters close to each other, since there's no training example showing how they are positioned relative to each other. So you might end up, let's say, with this blue cluster being positioned very close to the green cluster. And this is bad because if we now ask what is, please generate a recommendation for a green item, I might end up, for a green user, I might end up with a mix of green items and blue items. So blue items are, supposedly not relevant to this green cluster. And this is what we sometimes call folding. So if you're not careful, you're trying, so what you're trying to do is to learn a representation, a low dimensional representation. So these are low dimensional vectors, these embedding vectors of, a very large matrix. And what you could do is you fold this space onto itself, and you might end up with things that are near each other that are irrelevant to each other. Okay, hence the importance of taking into account these unobserved part of the matrix. All right, so now that we define this loss function, the next thing we do is we optimize it. And as I mentioned, there are general purpose methods to optimize the loss or to learn the model, such as stochastic gradient descent. One nice thing is that it's a generic method. For example, it can handle other losses. So if you care about something else, like let's say the softmax loss, that the cross entropy softmax loss that we will see in the next part of the lecture, you might replace this loss function by something else. It's also parallelizable because you can, as you know, you can run stochastic gradient descent one example at a time. However, it is slow on this particular method. So as we will see, there's much more specialized methods. And also the handling of the second sum is more tricky because the second sum, when you sum over the unobserved part of the matrix, there are many more observations. So this is all of the possible pairs between all of the users and all of the items. And an example like YouTube, this is huge, right? So there's 1 billion items, and there are maybe hundreds of millions or more of users. So now, on the other hand, you have more specialized method, and one such method is called weighted alternating least squares, or WALS for short. Now, the disadvantage is that it's specific to this loss, so it's specifically designed for the least squares loss, or this weighted version of least squares. However, compared to SGD, it's extremely fast. So one intuition of why this is fast is that it is a second-order method, so it will converge in very, very few iterations compared to first-order methods like gradient descent. And it also seamlessly handles these unobserved entries in the matrix. So for those of you who are interested in the details, you can look at this paper here. So it is a relatively old method, so it's from more than 10 years ago, so now almost 13 years ago. And it's still, in many ways, it is still the state of the art for the matrix factorization problem. Okay, so now that we looked at the details of how to learn the factorization for collaborative filtering, let me just quickly summarize some of the points about collaborative filtering. One of the main advantages, and I think the attractive things about collaborative filtering, is that you don't need domain knowledge. So as we saw, you can automatically learn these embeddings. You don't have to manually tune the features. And because it's using this simultaneous similarity between users and items, it can result in serendipitous recommendations. Now, some of the limitations of this model is that it's only bilinear. So remember, the model is the product of this U times V transpose. So you might argue that the modeling capacity is somewhat limited. So maybe it cannot handle some sort of nonlinear interactions between users and items. So you can define fancier models that are more expressive. And also the other question is, what happens if you do have features? So in the version that I just showed, it's only using interactions between users and items. So if you have features like, let's say, features describing the items or features describing the users, then it's not immediately clear, at least, how to extend this model to take those features as inputs. There are ways of doing this, but let's say in a neural network model, it's much more straightforward to do. Okay, so this takes us to the next class of models, which are neural embedding models. And so one motivation for this is exactly to address some of the limitations of matrix factorization, like introducing some nonlinearity in the model and also incorporating side features. So as a warm-up, before we look at more complicated models, we're going to actually try to reinterpret matrix factorization as a neural network model. So let's try to do this. Remember, we have this input matrix on the side again. So where one row represents a user, one column represents an item. And then we're going to think of this neural network where the input layer is as large as the users in your model, and the output layer is has as many entries as the items. Okay. And there's going to be only a single hidden layer. And this is a bottleneck model, so it has the hidden layer has much fewer entries than the input or the output. Okay. So now let's see what happens if I feed a one hot vector to this model. So if I want to generate predictions for this user, for example, so I'm highlighting this user, the row of this user on the matrix. If I want to generate predictions for this user, I just feed a vector that contains a 1 for that user and then 0 everything else. So I just select this user. And then the goal will be to predict a vector where the value, so a vector that's as long as there are movies in my corpus, where the value is close to 1 if that movie is in the ground truth, and is close to 0 otherwise. Okay. So this is the prediction of the model, and the check marks on top are the ground truth. And I want these two vectors to be close. Now, if I think more precisely about what this model is doing, let me just call the first matrix of weights U transpose and the second matrix of weights V. And it will become clear why I chose this, this notation. So now if we call them U transpose and V, and now I look at the prediction of the model for item J. Okay, so for this user I and for this item J. Then, so of course, for the first layer, because I'm setting all of the inputs to 0, except for the first user, except for user I, then I'm actually selecting just the vector ui. So these are all the weights connected to user I, or in other words, this is the ith row of the matrix U. And for the second layer, because I'm only looking at item J, so I'm ignoring all of the other items, the output here will be just all of the weights connecting J to the hidden layer multiplied to the corresponding weight from UI. Okay, and because so the output of the network is this weighted sum between the VJs and UIs, right? Where the weights are the VJs and the original vector is the UI. But this is exactly the same as taking the dot product. Remember, the dot product between the two vectors is I take the element-wise sum, the element-wise product, and then I take the sum. Okay. So what we're doing here is nothing else than the dot product between UI, which are all of the weights connected to user I, and VJ, which are all of the weights connected to item J. And this is exactly the matrix factorization model. It's just presented differently, presented as a neural network. Of course, this is a very simple neural network, so it has only 2 layers. It also has no nonlinearity, right? So the hidden layer doesn't have nonlinearity, but it is exactly the same problem. And then if we minimize the least squares loss using whatever method we, either SGD or alternating these squares, then we will have learned a matrix factorization model. Okay, so then because of this picture, you might think that there are ways of extending this. So for instance, what I can do is I can keep the output layer of the network. So I still want to predict a score for each movie such that the score is high for relevant movies and low for irrelevant ones. But I can change the bottom of the network. Okay, so the first part of the network, I can change it. And this is exactly what we're going to do. So let's try to design together some other neural network that now takes into account user features. Okay, and I'm going to introduce a little bit of notation on the side. So I'm going to call X, for example, the input feature vector for the user. Now, the advantage of this model is I could potentially feed other things, other features about the user to the model. Things like, so we previously used the user ID, so just one number per user representing that user. Now we can feed other things like history of watches, videos that this user previously watched, maybe text queries, maybe time of day, and other things. Another change that I can make is I can add some hidden layers, maybe to introduce nonlinearities. And I'm going to call the output of all of these hidden layers as psi of x. Now, the last part of the model, as I said, is not going to change. So I'm still going to call this matrix V, the last matrix of weights. And of course, the output of the model will be a vector, again, as long as the corpus. So one entry or one number per movie. Now, it's very common for such models to use, instead of outputting just a score vector, we can output a probability distribution over items. And one way to do this is to apply the softmax function. Okay, so this p hat of x is the output of the model. It's a probability vector. And it's this function s, which is softmax, applied to the output of the network, which is this psi of x times v transpose. Okay, so again, so one step at a time, psi of x is the output of the last hidden layer of the network. We multiplied that by the V matrix, so that's psi times V transpose. and then we apply the softmax function. What the softmax function does is it takes any score vector and it turns it into a probability vector. So a probability vector is something where all of the entries are positive and they have to sum to 1. Now, the specific form of the softmax function is very simple. So you take the exponential of the vector, and then you divide by the sum of all of the entries. So because you take the exponential, now the vector becomes positive, and because you're normalizing, it sums to 1. Okay, so it becomes a probability vector. Now, just as a side note, if you're wondering why it's called softmax, so you can think of this as in relation to the quote-unquote hard max function. So one way to do this is you can, so when you have a score vector and you want to assign it to turn it into a probability vector, what you could do is just assign probability 1 to the item that has the highest score and probability 0 for everything else. Okay, so it's a very simple way to do, but of course this has some issues, especially for training models, because this function is discontinuous. So it doesn't have a well-defined gradient, and we cannot apply things like gradient descent and so on. And also it introduces some instability. So it's not a good idea to use the hard max. So instead we use like a smoothed version of it, which is the softmax. So softmax still assigns higher probabilities to higher scores. So if you look at this expression on the bottom left, in the vector y, so the original vector of scores, if yi is larger than yj, then the probability of I will still be larger than the probability of j, because exponential is a monotone function, and then we normalize by the same constant for everybody. Okay, so it's still something that assigns higher probabilities to higher scores, but it's not assigning, like all of the mass to only a single item. It's distributing the mass across all promising items. Okay, so that was an aside about the softmax. So now, once we turn the output of the network into a probability vector, usually you want to define. Okay, so let me just. I don't think I defined the loss function here, but you will define a loss function where you compare the output of the network to the ground truth. So the ground truth, again, is a vector of, let's say, a binary vector where there's a 1 for each item the user consumed and a 0 for everything else. You can normalize this vector to make it a probability vector. So assign weight 1 over k for all of the k items that the user watched. Now you have these two vectors, and you can measure the distance between the two. And one way to do this, one common way to do this, is using the cross entropy. So this is why usually in machine learning libraries like TensorFlow, you will find these going together. So the cross entropy of the softmax. So you'll have cross entropy softmax loss. Okay, so the last thing I want to show about this model is also this interpretation in terms of embeddings. So we saw in matrix factorization, it was very explicit. So we are learning 1 vector per user, 1 vector per item. But I hope I can convince you that here as well, I am learning an embedding per user and an embedding per item. So let's look again at the output probability of one of the items. Let's call it item I. Okay. So we've done this exercise again in the previous 2-layer network. So let's do it here, and hopefully this will look familiar. So if I look at the probability for item I, this is the weighted sum of the vector psi of x, which is the last hidden layer of the network, weighted by this vector vi. Okay. But that's, again, just the dot product between psi of x and vi. Of course, the final output of the network still has the softmax transformation. But as I said, this is a monotone transformation. So things that have a higher score will have a higher probability. So at the end, this dot product between vi and psi of x still determines relevance. So something that has a high vi dot psi of x is more relevant than something that has a low dot product. So in other words, I can still say that vi is an item embedding. So it is a vector representing this item I, and psi of x, which is the output of the network of the last hidden layer, this is the query embedding or the user embedding. Okay. So another picture, so now if I go back to this original picture I had in this 2D vector space, on the item side, things didn't change. I still use one item, one embedding per item. What changed is how I learn user representation. So before I had one static vector or embedding per user. Now I'm learning a function, this function psi, mapping user features to an embedding, okay? And now if I change x, if I change the input features by feeding it the features of another user, then I might end up with a different embedding, with a different psi of x. Now, one advantage of this is that I could potentially generalize to other users, right? Because I'm learning this mapping from user features to an embedding in this vector space. So I don't have to have seen this user before to be able to generate an embedding for them, right? Whereas in matrix factorization, if I did not see a user, so if I don't have some history of things that the user consumed in the past, then I cannot possibly learn an embedding for this user. Okay. So this is known as the cold stack problem. So if you haven't observed a user, or on the other side also, if you haven't observed an item before, then you don't know how to learn a representation for them. Now, what I'm saying is not 100% true. We can always come up with heuristics to generate embeddings for users or items that we haven't seen before. For example, a very simple thing that you can do for an item is you might still have features about the item. For example, if I'm learning a movie recommender system, then I know, let's say, the genre of that movie. I may know the director of the movie. I may know the actors in that movie. So I can still use these features to generate a temporary embedding for that item. For example, by assigning it an embedding close to things from the same director or things with the same actors. Okay. So I have a way to bootstrap the system by assigning a temporary embedding. I can use that to collect some data. And then once I have observations, I can learn a more precise embedding for that item. So this is all to say that there are ways to solve the cold stack problem. Of course, it's a very sort of mature topic, and people have looked at this many times. But this generalization to user embeddings allows us to solve this cold stack problem too. Excuse me. Okay, let's take a 1-minute break and I'll be right back. Sorry about that. I'm back. Okay, so let's go back to our problem here. So we saw how this neural network model, or the softmax-based model, is one way to generalize our first model to a situation where we learn a mapping from the user features to the user embedding. So now you could also imagine actually doing the generalization on the item side. So you might also learn some other mapping, let's say some phi of y that takes item features y and maps it to an item embedding. So I'll let you imagine that kind of generalization. So this becomes more tricky, but it has been done in the literature, and you can look up things like two-tower models or like Siamese networks. So that's the idea there. So you have two networks, and the output is the dot product between the last layer of the first network and the last layer of the second network. So that's the psi of x and then phi of y. Okay, so here's my slide on loss functions. I didn't remember the order of the slides. So this is what I described before. So once we have the output of the network, this p hat, we want to compare that to the ground truth distribution p. And this p is nothing other than the row in the matrix. So here at the bottom right, I'm highlighting the corresponding row for this user. Right, so this has 3 items, and of course we can always normalize it to make this a probability vector. And then I compare these 2 probability vectors using some loss function like the cross entropy, as we said. All right, so in the next few slides, we're almost done with the lecture. In the next few slides, I'm going to discuss a set of topics that I think are important and that one should always keep in mind when designing a recommender system. So the first topic is the choice of an objective function. And for this, I like to quote one of my colleagues who likes to say that machine learning in general is like a mischievous genie. It will be happy to make your wishes come true, but you have to be careful what you wish for. And just to show what this means, let's consider a hypothetical example where I want to define an objective function for, let's say, a movie recommender system or a video recommender system like YouTube. And you might ask, okay, what should the model learn? Should the model learn to predict, let's say, to predict some measure of engagement? So one guess might be, okay, let's try to optimize clicks. So we know, for example, what users clicked on what videos. So can we teach the model to predict those clicks? So in other words, what do we fill this matrix with? Right? So we could fill the matrix, the ground truth matrix, with ones whenever there's a click. Now, if you think about this, I mean, you might be familiar with this problem, but this has issues. And the types of recommendations that this model might generate is something that, of course, will generate clicks. And what generates clicks is clickbait. So we know this notion of clickbait where, let's say, the video title or thumbnail or description might, want you to click make you want to click the video, but maybe the content is of very poor quality, or the content doesn't actually match what's in the title or in the thumbnail, or maybe it's just bad content that you will get tired of very quickly. So this may generate clicks in the short term, but of course it will make for very bad user experience. So instead of that, okay, we might think, okay, let's say if the issue is that this is generating clicks, but the users don't actually watch the content or get tired of it very quickly, what if we optimize watch time instead? So how long the user watches after they actually click, okay? Now, I'll let you think about this for a few seconds and think about any potential issues with this. So if you only optimize for watch time, then you might end up recommending something like this. This is a silent 24-hour countdown timer. This is an actual video on YouTube. So it's a video that has nothing for just a timer, a countdown timer for 24 hours. Now, of course, such a video will only be clicked with very low probability. However, because we're optimizing for watch time, This very long video with tiny probability will be treated the same as a much shorter video with much higher probability, right? And intuitively, I think it should be clear that these should not be treated the same. That we still want to favor shorter and more relevant content than just watch time. So at the end, we want to define some better measure of engagement. So maybe it's something that is session-based, so not just the next video, but maybe we look at the next few videos and we look at the average watch time and other measures of user satisfaction or user engagement over the next few videos. And something, this is something that's very complicated to do in practice, and it's a very iterative process, as you can see. So you might come up with the first measure, and then as you realize that it's flaws, you might change it, and it's a continually changing process. And hopefully it results in relevant recommendations and things that keep the user engaged. So here, I'm showing just shorter videos that are maybe on topic, rather than just very long videos or just videos that are generating clicks. Okay, so that was the design of the loss function. Now I'm going to talk about serving. So what we've seen so far is how do we train the recommender system. So how do we learn these representations for users and items? So now what do we do when the user comes to the website? So we talked about this a little bit, right? So the problem, one way to formalize the problem is given the query or the user embedding, we look for items that are close in the embedding space. So close according to the similarity measure, whether it be dot product or cosine and so on. And one way to do this is I can just compute the dot product for for all of the items, for all of the candidate items, so for all of the items in the corpus, and this is called exhaustive scoring. So I just exhaustively score all of the items. And even though this is just computing a simple dot product between two vectors, that can still be expensive if the corpus size is very large, and if you have to do this at every time a user visits your website or every time the user watches a video. So what we can do instead is approximate nearest neighbors. So instead of computing exactly the top nearest neighbors or the top scoring items, I can do this approximately. And there is a set of techniques called maximum inner product search. And this can be sublinear in the number of items. So it scales, as the log, I think, as the logarithm of the number of items. And this is based on hashing techniques. So you do some pre-processing on the item embeddings, and then you can query this with some user embedding, and it will give you the approximate nearest neighbors. So of course, this is mostly relevant for the second situation that I showed, right? So the second type of models where you learn a function that maps user features to user embeddings. So for the first situation, if the user embedding is static and the item embeddings are static, right? So they're not changing over time, then I can just pre-compute for each user. I can pre-compute the recommendations for that user by computing, I can compute offline all of the dot products, and then I can store them in some lookup table. And then every time the user comes to my service, I can show the recommendations for this user. I can just, look up from this table what are the top K. So I don't need to recompute things on the fly. But of course, most engaging services will have some dynamic recommendations. So the second situation is more relevant, where maybe every time the user comes to the website, I will generate different recommendations based on a different embedding vector C of x. So I have to recompute the user's embedding every time they visit, and then I have to regenerate new candidates. Okay. Yes, so this is again so the architecture. First, I store the embeddings in some server, And as I said, you do some pre-processing based on hashing. And then when you query this with some user embedding, it will return the .k items. So another important topic is how do we make sure that the recommender system is recommending more than the popular content? So one very easy thing that the model can learn is what items are popular and sort of always recommend those items. So one solution is that, and so let me just say one thing, that this can happen if you're not careful, because popular item, sort of by definition, are consumed many more times than more niche content or more rare items. Okay, so think of a video in YouTube, for example, that has tens of millions or hundreds of millions of views, compared to another video that has very few views, like maybe hundreds or thousands, right? So in this giant matrix that we created, this ground truth matrix, so one of the videos will have a lot of ones, and some other videos will have very few ones. Now, if you look at the contribution of the popular video versus the niche video to the loss function, one video will have many more terms in the loss than the other video. Right? And if we're not careful, it's possible that the model will learn very well the representation of the popular video, but will not learn the other one. Okay, so that's why we might want to do some weighting of the training example. So we assign weight, we downweight the popular content and we upweight the niche content. Okay, so that's one way to do it. The other way is we might use more features, so more item features or more user features that can help capture relevance. So if the model, doesn't have a lot of features, then it might sort of default to recommending the popular content. On the other hand, if it has enough features, if it has enough capacity to capture the interests of certain users, then it might be able to go beyond this popularity signal. And the last thing I want to mention that we will actually see during the collab exercises is using a different similarity measure. So instead of using dot product as a similarity measure, you could use cosine, for instance. Okay. So in the parentheses, it should say cosine instead of dot product, not the other way around. And to give you some intuition about this, is we will see that if you learn a matrix factorization model, for instance, the norm of the embedding is usually highly correlated with the popularity of the item. So items that have more observations will have a higher norm of their embedding. Why? Because again, if you look at the contribution, so at the number of, so let me actually go back to one of the previous slides on matrix factorization. And we can look at this matrix together, this matrix. So think of one item that has a lot more ones. So one column that has a lot more ones than another column. So we're asking the model to predict one much more frequently in one case than the other case. Now, one way to do this is just to scale up the embedding for one of the vectors. Why? Because the output of the model is just the dot product between the user embedding and the item embedding. So if I fix everything else and I just take the items embedding and I scale it up, then I'm just going to scale up the prediction of the model, right? So I can be much closer to one than with an embedding of smaller norm. So that's why we see this kind of correlation between number of observations and embedding norm. Now, as a consequence of that, when I'm computing the scores of a candidate, a popular item or an item with more observations will tend to be recommended more frequently if I'm computing dot products. However, if I use cosine instead, then I am discarding the norm, right? So I'm only looking at the angle between the vectors, and I'm not looking at the norm. So then I can drastically reduce this popularity signal or this bias towards popular item. Okay, So now let's go back to here. So that was the handling of popular items. And we'll actually experiment with this during the collab. So we'll see how changing the similarity measure can change the behavior of the model. So the last topic is how do we handle new items, or the so-called cold stack problem. And I already talked about this a little bit. So what to do if an item is not seen in training, or the same thing for a user, right? So one sort of obvious solution is just to retrain the model as often as you can. And of course, every time you retrain the model, you don't want to retrain it from scratch. You can warm start it from the previous version of the model. So for instance, if we're talking about items, I can, if there are new videos, let's say, that were uploaded to my service, I can take all of the videos that already existed in the previous version of the model, and I can initialize the V matrix, right? So the item embedding matrix. I can initialize the embeddings for the existing items to their previous value from the previous model. And then for new items, I initialize them randomly, right? And then I let training continue. So that way, I don't have to relearn everything from scratch, and my model will generally converge in much fewer iterations. So another way to solve this cold stack problem is to use models that have item features. And as I mentioned, this can be more tricky, especially for the candidate generation stage. And then the last thing, which I already mentioned, is to use heuristics to get new item embeddings. So we assign a temporary item embedding to some new item based on their features, based on things like genre, director, actors, and so on. And then once we collect some interactions, some data, we can actually learn a better embedding for those items. Okay, so that brings us to the end of the lecture. So just to summarize what we saw so far, we saw, if there's one thing that I would like you to remember from this lecture so far, is that the main strategy to learn recommendation models is to learn this embedding representation of users and items. So many of the models can be pictured in this way, can be understood in this way. So perhaps the simplest example is matrix factorization. So we saw that we learn a static embedding for users and items. And we saw how to do that automatically without relying on features. And then neural embedding models, in some sense, generalize this picture, where you can learn mappings from user features to user embeddings, or similarly, mappings from item features to item embeddings. But at the end, many of these models still take, let's say, the dot product between the user's embedding and the item embedding, and that dot product is the measure of relevance or similarity. Okay, so with this, let's take a quick break. So let's take a 10-minute break, and or let's actually make it 5 minutes, since you can always pause the live stream if you want to take a little longer break. So during this time, I'm going to check if there are any questions, and I'll be back in 5 minutes. I'm going to eat a little bite for breakfast. It's early morning for me, and then I'll be back. And in the next section, we'll be doing the collab exercise where we will build a simple movie recommendation engine. So if you'd like to take a look, a quick look at the collab, go to this link, and then I'll go over the details when we come back in 5 minutes. All right, I'll see you soon. Hi, hello, and welcome back. We're going to continue together for the next hour and a half or so. So I took a look at the socio Q&A session. For now I only see one question, and so Khadija is asking, how can we know the values of U and V? And I think this question was probably asked very early on. So hopefully it became clear how you can learn these matrices, these embeddings U and V automatically. So of course, we saw two examples. One is content-based filtering and one is collaborative filtering. In content-based filtering, you can manually, in some sense, learn U and V. So U and V can be the features of the items. And for the user, you can assign also the same embeddings based on the items. In collaborative filtering, you can learn them automatically by solving this optimization problem. So let me show it very quickly one last time. So this is an important point, so it's good to drive this point home. So one way to formalize the problem again is to say that we have this ground truth matrix A, and we want to learn automatically learn two low rank matrices U and V transpose, such that their product is close to the ground truth matrix. How to do this is we can define a loss function and then optimize that loss function. So the loss function that we saw, that we settled on, was this combination, this weighted least squares loss, where we weight the observed and unobserved parts differently. And then we optimize it using either stochastic gradient descent or more specialized methods like alternating least squares. Okay, so maybe I will also mention one thing about this problem, right? So there are a few hyperparameters that I haven't talked about that we will see during the collab. So one that's apparent is this alpha here, is the weight of the unobserved part in our loss function. So that you can treat as a hyperparameter, so you can do the typical cross-validation procedure to choose the value of alpha. Another one that's important is also the embedding dimension, so the dimension of the vectors representing users and items. So in our toy example, it was a two-dimensional vector, so we can draw the vectors on the plane. Of course, in practice, you will use a much higher dimension. However, you won't go very high. So in typical applications, you'll use a dimension of maybe 100 or a few hundreds. I have rarely seen applications where we go much beyond that. And that, again, you can treat as a hyperparameter. So typically, we should see that with a higher embedding dimension, the quality of the model becomes higher. Of course, there's a little bit of risk of overfitting if you go very high, but with proper regularization, we should always be able to get better quality, or maybe it will flatten at some point. However, there's also a cost for increasing the embedding dimension, because now when you're at inference time, when you're evaluating the model, you also have to take dot products of larger vectors. And that directly translates into computational cost. So usually there's this trade-off that you want to make between better quality and higher computational cost. Okay, so with that, let's now switch to the collab. So I hope most of you have clicked on this link, went to this link. So it's bit.ly/rexiscollab. So let me open it. And I think I need to also change the sharing to this. Okay. Okay, here we go. All right, so once you go to the link, you should see this collab. And let me give you a quick overview of what we will be doing. in this collab. So the goal is to train a movie recommender system, and this is based on a data set, on an academic data set called Movie Lens. Okay, so this is a set of ratings from users, between users and movies. Okay, so it's very much like the example that we saw. The only difference is that the ratings have a value, a numerical value between 1 and 5. So each user will rate a subset of the movies, and to each movie they will give some number between 1 and 5. Okay, so it's very much like the matrix that we saw, where one row of the matrix is a user and one column is an item. All right, and so in the interest of time, we're going to train the simplest model, which is matrix factorization. But we will see, we'll spend a lot of time looking at the effects of the choice of certain parameters, things like embedding dimension, like the regularization constants, like what happens if we don't take into account the unobserved entries of the matrix. And we will also look at different techniques to inspect the model. So what can you do beyond looking at usual things like the value of the loss function? Okay. And so we're going to be using Colab. If you're not familiar with this tool, so this is a website where you can basically run Python code in the form of an IPython notebook, and it also comes with a backend. So you can check, so you can select the runtime by clicking runtime and then change runtime type. Okay, let me zoom in a little bit to make sure that everyone can read this. So if I click runtime, change runtime type, so you can either select none if you just want a CPU instance. You can also pick GPU, which is what we will be using today. So even if you can't, depending on availability, you may or may not be able to get a GPU. So if you can get it, that's fine. All of the code will run fine with GPU without an accelerator. The only difference is that it may be a little bit slower. Okay, so then you can save. And then you go to the top right here and click connect. This will allocate an instance for you. And then hopefully we should be good to go. Oh, so one more thing that I forgot to do is it's good to, so you may have noticed that changes will not be saved because I'm editing directly the sort of the master copy of this file. So I'm just going to save a copy in Drive, and this will create a copy of this collab that I can edit, and now changes will be saved. Okay, so make sure to make a copy if you want your changes to persist. Okay, so I'm actually going to switch now to this other tab. Or I will just edit this copy. Yeah, it doesn't matter. Okay, so now once I have made a copy and I allocated the Colab instance, so another thing that I will advise you to do is make sure to run all of the cells. So there's a little bit of outline at the beginning. Now the first cell, so each code cell, you can run it by clicking this button, this play button, or you can also click Control Enter or Command Enter if you're on Mac. Okay, so the first cell will import a few libraries and also download the data from the Movie Lens website. Okay, so once we run these, this takes a few seconds. And so another thing, while this is running, if you want to look, some of the code cells will be hidden. For example, the importing of the libraries at the beginning. So if you want to look at the code for a given cell, you can either double click it, and this will expand it, or you can also go to the three dots on the right-hand side, and then you can choose, I think, hide form, and this will show you the entire code. Okay. So there will be exercises throughout this collab where you can, at any time, you can pause the video and you can think about the code and write your own solution. And then I will go through the solution every time. Okay, so let me now collapse this. But every time, make sure to run the solution cell, because this will define some functions that will be used later. So sometimes, if you forget to run a certain cell, it's possible that some other cells downstream will not run correctly and will give you an error. So if that happens, make sure to go back and make sure that you run all of the cells. Okay, sounds good. So in the first few minutes, we're going to spend a little bit of time looking at the movie lens dataset. This is actually something that's good to do for any machine learning problem. So before you start working on the problem, it's good to get to know your data. Okay, so look at maybe some distributions of the data, and this is what we're going to do. So first, let's look. So first of all, this data set comes into 3 data frames. If you're not familiar with data frames, so it's called a pandas data frame. Pandas is a data processing or data science library. And a data frame is basically a table where each column is a feature, and just think of it as a table. And so for the first, so the data comes in 3 data frames: one describing the users, one describing the movies, and the last one describing the interactions between users and movies. So these are the ratings. Okay. So if you look at the first data frame, the users, this has the following features. We have user ID, so this is just a number. We have the age, the sex, the occupation, and the zip code of the user. So we do have additional features, but for the purpose of this collab, we're not going to use any features. But of course, later, if you want to revisit this collab or this model, you can try to expand it actually and define a model that uses user features or item features. Okay, so so that's the user's data frame. Then we can, what we do next is we're visualizing the distribution of the ratings per user. So here we're looking at the ratings data frame. And okay, here I'm showing 2 things. One is the histogram of the number of ratings per user. So the way to interpret this plot is that most of the users on the left-hand side here have fewer than 100 ratings. So that's the majority of the users. And then there's a tail of a few users that you can call, for example, heavy users. So there are some users that have more than 700 ratings. So this is something to keep in mind as you're training the recommendation model. I described the same thing for the items, right? So there may be some videos or movies that are much more popular than others, but actually the same thing happens on the user side. You might have users who are much heavier consumers of the content than others. And if you're not careful, it's possible that you might better serve the heavy users than the light users. And that's not good. That's not good for many reasons, for fairness and so on. So one thing you can do is also try to reweight the users by number of interactions. This is not something that we will do in this collab, because I think to some extent in the movie lens data set, it's not, the distribution is not too heavily skewed, but in real products, it can be much worse than this. And on the right-hand side is the distribution of the user rating. So this is the average rating assigned by the user. So it looks like most of the users, their average rating is around 3.5 or 4. But there are users who are very sort of generous. Their average rating is close to 5. And there are users who tend to give lower ratings. So this is just to show that, that's also something that depends on the user, sort of what they consider as a good rating versus a bad rating. All right, and next we do the same thing on the movie side. So here, the first thing that we're doing is kind of finding out which are the most popular movies. This is something that's good to keep in mind, because as I said, one common pitfall of recommender models is that they might, just recommend the popular stuff. So either the most highly rated stuff or the stuff that has the most ratings. And these are the two ways we're sorting the movies. So this is by number of ratings. It looks like in this data set, Star Wars got the most number of ratings, and then followed by a few other popular movies like Contact, Fargo, another Star Wars movie, and so on. So one thing you might notice about this data set is it's actually quite old. So most of the movies are from the 90s or earlier. And so one thing to know about the MovieLens website or the MovieLens group is that they make available different versions of the MovieLens dataset. And this is the smallest one. And I think the earliest one as well. So there have been later versions of this that contain more recent movies, but also more ratings and more movies and more users, right? But just for the purpose of time and efficiency, we want things to run fast in Colab. So we're going to use the smallest data set. But actually, with more time and maybe a more careful implementation, you can run on the later versions of MovieLens. So that's an exercise that you can go through if you'd like. If you start thinking about scaling this to larger problems. And let me scroll back up for a second. I think at the beginning we printed some basic statistics about this. So just to give you a sense of the scale, this dataset has about 1,000 users and about 1,600 items and 100,000 ratings. So it's a relatively small problem compared to things that I've been talking about. And this is the reason why we can run things very fast in Colab. Okay. So now we do the same thing. So we rank the movies again. This is by number of ratings. And then by average rating. Okay, so the top movies by average rating have, about 4.4 or 4.5 average rating. And this is something that I always find sort of funny or interesting about this data set. Maybe some of you will recognize some of these titles. So A Close Shave, and I think The Wrong Trousers, and this movie, this might be a documentary or something, are movies from Wallace and Gromit, which is this stop motion clay animation show from the 90s, which I really like. I used to enjoy them. However, I always find it surprising that 3 of the top 5 movies in this data set are Wallace and Gromit movies. I mean, I love the show, but I wouldn't say that it's in my top 3 all-time favorite. So it's interesting. It's a little quirk of this data set. Of course, those have fewer ratings, even though they're not too rare, but they have much fewer ratings than the popular ones like Star Wars and so on. Okay, so now that we looked at the popular items in our data set, we can do the same thing as we did for the users. So here we are displaying the distributions, the histogram of number of ratings per movie, and also the average rating per movie. So the distribution looks actually quite similar to the user side. It's also the case that most of the movies have less than 100 ratings. And then some of them, as we saw, like Star Wars, have more than 500 ratings. So here again, the skew in the distribution is something to keep in mind and potentially try to fix. Now on the average rating, so here we're doing a fun little exercise where we're looking at the average rating per genre. So the movies have, I think, genre and year as extra features. So each movie can have multiple genres. So now if you select on this chart here, if I select a genre, for example, action, then this will show me the distribution for the action movies compared to the average distribution. So here you should think of this plot as the superposition of 2 histograms. So one in blue and one in kind of transparent gray or translucent gray. So think of them as two distributions on top of each other. So here you can see how the distribution shifts as you look at specific genres. So for action movies, it looks like, it's a little bit lower than average in general. Adventure looks perhaps similar. It almost looks bimodal, where some people, tend to give low ratings and some people tend to give high ratings. Children movies looks a little bit lower overall. Let's see, if we look at fantasy, so this might not have many ratings. I think there aren't that many fantasy movies in this data set. Sci-fi maybe tends to be a little bit higher, and so on. So this is just an indication that genre might contain some useful signal, right? So using genre features, you might be able to improve the model. This is again something that we will not do together, but you can explore later. So the features are in the data set. We're just not going to use them. Okay, so that was our quick quick tour of our data set. And now we're going to start preparing for the training of the model. So here's, again, a little bit of notation. Remember, the goal is to approximate this matrix A by the product of two matrices U and V transpose. You should think of U as the stacking of all of the user embeddings. So U1 is the embedding for user 1 up to UN. The same thing for V, it's the movie embeddings. Okay, so the other notation is not very important, the number of users, number of movies, etc. Our first exercise is going to be writing a sparse representation of the rating matrix. This is something, as I mentioned, the observation matrix in general in recommendation are sparse. So we don't want to represent the full dense matrix with all of the zeros in it. So instead, what you can do is just represent the non-zero items in the matrix. And there are different ways of representing this. In TensorFlow, which is what we will use in this collab, there's this notion of sparse tensor. And one way to think of a sparse tensor is just a list. If you look at the example here below, if I have this matrix A, right? So it's a matrix of zeros, but that has three non-zero entries. To represent it as a sparse tensor, I can just list the non-zero entries in this matrix. Okay, so here there are three. So here I have three elements, and for each element I need to specify three things: the row index, the column index, and then the value. Okay, so the row index is the same thing as the user ID. Remember, rows are users. The column index is the same thing as the movie ID, and the value is the rating. So this will be a number between 1 and 5. And that's it. So that's essentially it. Conceptually, that's what we're going to do. We're just listing all of the non-zero entries in the matrix. Now, the way to write this in TensorFlow, for those of you who are familiar with TensorFlow, you can listen to me more carefully. If you're not familiar with TensorFlow or you're not interested in the implementation details, you can skip these details, and that's fine. So, what I want you to get out of this collab is more about the practice of training recommender systems than the actual code. So many of the principles that you'll see here will translate across libraries. So it doesn't matter which language or which framework you're using. So that being said, in TensorFlow, you can write this as a sparse tensor where you specify the indices, which are, for each entry, it's the row index and then the column index. And then the values is, again, the rating value. So here we will have three pairs for the indices, 0, 0, 0, 1, and then 1, 3, and then three values. The other thing that I need to specify is also the shape of the underlying matrix, because sometimes it's not possible to infer the shape just from the indices and values. For example, if there are missing if there are columns or rows that are completely empty. And the first exercise is going to be to write a function that takes this ratings data frame. Okay, let me show you the data frame one more time. So if I look at ratings, so you see this is a data frame that contains the user ID, the movie ID, and then the value of the rating. There's also a timestamp, but we're just going to ignore this, right? And this is more or less the sparse representation that we want. right? So the first exercise is just to turn this pandas data frame into a TensorFlow sparse tensor. Okay, so this is just a little bit of warm up to get you, manipulating data frames and sparse tensors. So here's a code stub. So at this point, you can pause the video, pause the live stream, and think about this for a little while, how you'd write this. And then I'll go over the solution together. Okay, so if we look at the solution, all right, let me make sure that I have the code visible. Okay, so this function takes ratings, which is a data frame, and now we just need to feed this, feed the right fields into the sparse tensor. So for the indices, so if you're familiar with Pandas data frame, one way to select a column is just to write the name of that column, and then dot values will turn this into a NumPy array. Okay. So for our sparse tensors, the indices are the two columns, user ID and movie ID, and then the values is just the rating column. Okay, and then we cast this as float 32 because I think the original ratings are integers, I believe. Okay, so with that, we just create the sparse tensor, and the dense shape is, so we need to specify the shape of the underlying matrix, which is number of users by number of movies. Okay, so that was a simple exercise. Again, if you're following along, don't forget to run this cell. Now, the next exercise is to actually define the loss function that we will minimize. And for our first attempt, we're going to train different versions of this model. The first version will only train on the observed part of the matrix. So we want to actually see what happens if we kind of don't take into account the unobserved part. Okay, so here's, I want you to just focus on this equation. So the mean squared error between the matrix A and this reconstruction, this prediction of the model UV transpose, is just the average mean squared error, which is the difference. So I sum over all pairs ij in this omega, which is the set of observations of the ground truth. This is the rating value minus the prediction of the model. Squared. Okay. So in the next exercise, we want to write a function. Okay, so here Colab is complaining that I'm not using a GPU. We will get to that soon. So I hope it stops complaining. All right, so for this exercise, we will write this function, sparse mean squared error. That takes three things. So it takes the sparse ratings, which is the matrix A. It takes the user embeddings, which is the matrix U, and the movie embeddings, which is the matrix V. And with these three things, we want to implement this equation, essentially. Okay, so for this, there are a few TensorFlow operations that can be useful. One is gather ND. So this, basically, given a tensor and a set of indices, it will gather or it will return, the values from the original tensor corresponding to those indices. So here there's a link to the TensorFlow documentation. If you're curious, the second function that we will use is this tf.losses.mean-squared-error. Okay, so once again, feel free to pause this and think about the solution for a few minutes, and then I'm going to go over the solution. All right. All right, so let's see. There are actually many ways of doing this. Perhaps the simplest way is just to say, okay, first, let's actually create the full prediction matrix. So I take U and V, and I actually compute the full U times V transpose. And then I take the difference between A and U times V transpose. Okay? And this is exactly what the solution is doing. So I take the matrix multiply, this tf.mapmul, between the U matrix and the V matrix, and I want to transpose V. So that's my convention. I compute U times V transpose. Okay, so this is the full matrix of predictions. Now, because we only care about a subset of those matrix, only the things that were observed in the original sparse tensor, what I can do is I can gather from this full prediction matrix the indices that are relevant. And those indices are exactly the indices from the ratings matrix, the A matrix. Okay. So once I have this gathered, these are the predictions corresponding to the non-zeros. Now I have a list of predictions, and I also have the list of ground truth ratings, and then I can just take the difference between the two and the square. And this is what the mean squared error function does. So I do tf.losses.mean squared error between the values from the ground truth and then the predictions that I just gathered. Okay, and that's going to be my loss. All right. So now you might have noticed that this can be inefficient, especially for larger problems. So because our problem is small, this is fine. But creating the full prediction matrix, so computing this U times V transpose, in some problems, this can be a huge matrix that may not even be that we may not even be able to fit in memory. Why? Because this is the full matrix of number of users by number of items, where what we're really interested in is just a small subset of this matrix, because the ground truth observations are very sparse. So if you're curious, I'll let you think about how you would implement this in a more efficient way at scale. So basically, you only want to compute the products, the dot products between UIs and VJs for a given list of IJ. So for IJ in the sparse ratings dot indices. This is also something that's easy to express in TensorFlow, but I'll leave it as an exercise because it's not relevant for our scale. Okay, so again, make sure, and I should make sure to run this cell as well. Okay, so now with these portions, we are actually ready to train our first matrix factorization model. So for this, we're providing a class, this so-called CF model class, that works as follows. So let's look at this example usage. So first, we need to define a U variable, a V variable. So this is what the model will learn. Then we define the loss function. And then we create the CF model that takes U and V and then the loss. Okay, and what this basically does is it does a little bit of bookkeeping. It will generate some plots, and then you can train this model. And what this will do is it will just apply gradient descent. Okay, so here we're not going to bother with like the specialized implementations like alternating least squares, because the problem is small enough and gradient descent will do just fine. And also, this is doing full batch gradient descent, so it's actually computing the full gradient of the full matrix at each iteration instead of stochastic gradient descent. So you can try implementing SGD as an exercise to see how that changes, but again, the problem is small enough that we don't have to do mini batching. Okay, so yeah, if you're curious, you can look at the implementation of this class, but it's mostly doing some basic bookkeeping, some plotting of the losses, and so on. Okay, so make sure to run it. All right, and then now we're ready to put these pieces together and write our first or train our first matrix factorization model. Okay, so for this, you have another code stub that it's this function called build model. So it takes a few things. One is the ratings data frame. So this is the original data frame that we have to turn into a sparse tensor. And then it takes some hyperparameters. So let's go over these together. One is this embedding dimension, which is basically the dimension of the embedding vectors, right? Or in other words, the size of the or the rank of the U and V matrices. Okay, so this is a hyperparameter, as I mentioned. We can try changing that. It takes okay, these two parameters for now, yes. So I'm going to ignore these parameters for now, this regularization coefficient and gravity coefficient. So these we will come to later, where we change the loss function by adding this regularization and taking into account the unobserved. But for now, let's see what happens just with the loss we defined so far. And the last hyperparameter is this initial standard deviation, which is how to initialize the two matrices U and V. So we're going to initialize them randomly using a normal distribution with this given standard deviation. Okay, so I'll give you a take a look at this code. Feel free to pause the video and think about the solution. And here I will go over the solution together. All right, so the first thing we will do is we split this data set, so the rating data set, into a train set and a test set. So this is, of course, always good to do. So you train the model on the training set, and then to look at generalization. So you try to, you estimate, for example, the losses and any other metrics you care about on the test set to see if there's a big gap in performance between training and testing. So it's possible that you might be overfitting, for example, and even though the train error is small, the test error might be large. So here we're splitting, so we're providing this kind of utility function that will just randomly split a data frame. And this holdout fraction means that we're keeping 20% of the observations as test ratings and everything else as train ratings. Okay, so once we split the data frame, we just turn this into a TensorFlow sparse tensor by calling the function we defined above, this build rating sparse tensor. We do the same thing for the test. Then we create our two variables. So we're calling them U and V. So this is using a TF variable. So you need to give it its initial value. As I said, we will initialize them using a normal distribution. And we need to specify the shape or the dimensions of each of these matrices. Okay. So for the U matrix, it should be number of users by embedding dimension. So this is what we're saying here. So it's the same. It should be the same shape as the number of users, which is the first dimension of the ground truth matrix A, by embedding dimension. And for the V matrix, it's number of movies by embedding dimension with a given standard deviation. Okay. And then, so for the train error, we compute the sparse mean squared error for, so applied to the train matrix and then the U and V. And for the test error, we do the same thing, but we just change the first argument to a test. Okay, and then I'm going to skip this. I'll come back to this part later. And so let me just comment this. And then the total loss is just going to be the train error. Okay, so let me do this and comment this. And then we're also going to show a few other, so we will visualize these metrics, so this train error and the test error. Okay, let me skip this for now. And I'm also going to show recall. So recall is, so basically looking for each user in the train test or in the test set. So for each user, we want to ask basically, so among the top movies, the top scoring movies according to the model, which ones were actually rated by the user. So here we're basically taking a different look on the problem, where instead of predicting the ratings in the original matrix, we're going to say, is the model able to distinguish between something that the user rated and something that the user didn't rate? So it's more of a classification problem. Okay, so it's a binary classification where the model is trying to guess which movies were rated and which were not. So this is sort of a proxy to know, to basically say which items are relevant and which are not. So these two abilities, I mean, these two metrics, the squared loss and the recall, are measuring two different abilities of the model. So one is the ability to, between relevant items, to distinguish which ones have a higher rating than others. And the other one is the ability to distinguish which ones were rated and which ones were not. And both are important, as we saw in the lecture, right? Because if you completely ignore the second part, if the model is not able to know which items were rated, then it may, predict anything on the unrated items, and this will not be penalized in the loss function. All right, so we're also given, we will also plot this recall to be able to evaluate kind of the second ability, this distinguishing of the observed versus unobserved. All right, so I hope my changes didn't break anything. So with this, I think we're ready to train our first model. So we will call this build model function on our ratings data frame with some embedding dimension. Okay, let's start with a low embedding dimension. Let's say our embedding dimension is 3, with some value for initial standard deviation and with some value for the recall. So this is just saying, compute the recall at 20. So among the 20 top scoring items, how many were so how many positives did we get right? Okay, and then, so once we build this model, we can do model.train for a certain number of iterations and with a certain learning rate. So this is, again, plain gradient descent. Here I did, just a minimal amount of tuning. I think you can probably get better performance by iterating for longer. So let's say 2,000 iterations. Okay, now it's the moment of truth. If the code runs, it means I didn't make any breaking changes. Okay, so it looks fine. So it's training. All right. So a few things that you will observe. So first of all, this is very fast because the problem is small. It might be slower. It will probably be slower if you're running on CPU, but especially on GPU, it's very quick. So you can train the model in a matter of seconds. So now, a few things to look at when you're looking at these plots. So first of all, the value of the loss function. It seems, okay, so if you look at the train error and test error, so the train error is 0.7. So remember, here we're trying to predict a rating with a value between 1 and 5, right? So 0.7 seems reasonable, right? It's not too bad. It's within, less than 1 star rating on a scale of 1 to 5. The test error, as we expect, is a little bit higher than the training error, but it's not also, it seems reasonable. Now, the recall is more interesting, right? So it has this behavior where for the first few iterations, it's going up, both the train recall and the test recall, and then it starts going down, right? And it seems like, if we keep training for longer, it might, go down even lower. So this may seem surprising at first, but after all, this is, we're not asking the model, we're not actually training the model to distinguish positives and negatives. So for now, we're only training the model to train the observed part of the matrix. So this is to drive home the point that the model might be, in a sense, overfitting to the observed part of the matrix. So it's not caring about what the prediction looks like on the zeros, on the unobserved part of the matrix, okay? So this you can already see by looking at the recall, but hopefully we should be able to see this in some other ways. So this is what we will do next. But before we do that, I'm just going to spend a few minutes looking at what happens if, for example, I change the embedding dimension. Let's say now I increase the embedding dimension to 10. Let's see what happens. And for this, let's try to remember, actually, let me just create a copy of this so that we have the values for both. Okay, so I'm training with embedding dimension 10 now. Okay, so let's see what happened on the train and test error. So the train error, as you might expect, went down, right? So if you increase the embedding dimension, you're increasing the capacity of the model. So now you're training, larger vectors for each item. So it should be able to fit the training data better. So the train error was about 0.7. Now it's 0.5. But the test error went up significantly. So now it's, almost double or more than double of the training error. So now the gap, the generalization gap, is increasing. And also it looks like the train recall and the test recall went down slightly, but they still have sort of a similar behavior. And these values are, by the way, quite low for recall. So it seems that even, embedding dimension 10 is pretty low. And even at embedding dimension 10, we're already seeing kind of a lot of overfitting. So I wonder what happens if, let's say, I go down even to embedding dimension equals 1. So if I were to do, let's say, cross-validation of the embedding dimension just on the test error, if I just look at the test error and I try to use this to choose a value for the embedding dimension, I think it actually looks like, okay, so 1 is slightly higher, right? So it's 0.92 compared to what we had before, 0.88. So let's see if I try 2. So the point that I'm trying to make here is that the test error is probably the lowest around a very small value, around maybe 2, 3, or 4. So, okay, here we're getting something 0.884. So it's already, embedding dimension 2 is already lower than embedding dimension 3. So I think, if I'm not mistaken, I think 2 will be optimal or close to optimal just on this problem with this loss. So this suggests that there's an issue. So it's saying that according to this criteria, the best model has embedding dimension 2. So there's clearly something that we can do better. All right, so with this, let's try to inspect the model a little bit further. So now we looked at the losses, which is great. But we can also try to, understand what the model is actually recommending beyond, on some examples. So for this, one way to do this is to say, okay, let's look at recommendations generated for a given user. So what you could try to do is, let's say, you generate some ratings for movies, and then you ask the model what are the top candidates for these ratings, right? So that's an exercise that you can do actually, and it's kind of a fun exercise because you will get to generate recommendations for yourself and see what the model comes up with. But that will take some time, so we're not going to do this. Instead, another thing that you can do is you can ask what are the nearest neighbors for a given movie, right? So we should be able to see that the model, places similar movies near each other in the embedding space. So if I ask what's the nearest neighbor of, let's say, an animation movie, hopefully I will see that the nearest neighbors are other, contain a lot of other animation movies that tend to be watched together by the same users. Okay. So, and this is what we are going to do. The way to do this, first, we need a function that computes the candidate scores, right? So this is given a query embedding U. So this can be the embedding of the user or the embedding of a movie. And given the matrix of all of the candidates, this V matrix, we want to compute all of the scores, okay? And as we discussed in the lecture, there are different similarity measures. The most common ones are dot product or cosine. And here's the, as a reminder, so the dot product, you can do this in NumPy using np.dot. Okay, so to compute the product, this is actually the matrix product, but for two vectors, this is the same as the dot product. And for cosine, you can do this by taking the dot product and normalizing by the norms of the two vectors. All right, and this can be done using np.linalg, linear algebra.norm. Okay, so this is the function that we need to write. Take a moment to think about the solution, and then let me explain the solution next. Okay, so we have this compute scores function that takes the query embedding, our U vector, the item embeddings, the V matrix, and it also takes a measure. So this can be either dot or cosine. Okay. All right. So what we need to do, remember from the so remember that the dot product, between a vector and the full item matrix V. Okay, let's see. Perhaps I can use. I can quickly use this board here. All right. So we want to compute the dot product between this embedding vector U, which is the query, and then all of the candidates V. Okay. So if I put this all of the candidate vectors as a matrix V transpose, right? So each column of this matrix is one candidate. So this is V1, V2, etc., up to Vn. So okay, let me just adjust this a little bit so everyone can see. All right, so we want to compute the pairwise dot products. So U dot product of Vi for every I. Okay, so now if I do this in matrix form, this is the same as taking, so the first dot product will be U by V1. So this is U dot V1, etc., up to U dot product with Vn. But this is exactly the same as the vector matrix product between U and V transpose. Okay? So this is exactly what we need to implement, just a vector matrix product. All right. This is the only point that this exercise is trying to make, kind of how to vectorize this computation of candidate scores. Okay. So with this, now let's go back to the code. So just to use the same notation, let's rename this query embedding to the U vector and this item embeddings to the V matrix. Now the only difference that between using cosine and dot product is, as I mentioned, you need to normalize when you're using cosine. So if the measure is cosine, we need to divide the matrix V by the norms of the columns, right, of the V matrix, because there's one item per column. So to compute the column of the norms of the columns, we can write np.linalg.norm of V and specify axis equals 1. Axis equals 1 means we're computing norms of columns. Okay, and then we do the element-wise division. So that will normalize columns. And for the U, it's just a vector, so we divide U by its norm. So that's normalizing U. And then the vector of scores is just the matrix vector, the vector matrix product between U and V transpose. So this is, a very compact way of writing this in NumPy. And then we return the score vector. All right, so let's run this cell. Okay, and now we're ready to compute the nearest neighbors for certain movies. So for this, you need to run this cell. If you're curious, you can look at the code here. But it's doing, it's doing a little bit of just string matching. So if you give it a title, then it will find the first movie, I think, that matches, that substring. It will look up the embedding of that movie and then compute the scores using the function that we just defined, right? And then among those, it will take the top k, where I think, k you can. Let's see, does it have k argument? Yeah, so k default to 6, but you can look at more candidates if you want. All right. So now let's look at a few queries. here I'm looking at the nearest neighbors of the movie Aladdin. So this is a Disney movie. It's an animation children movie. And okay, so according to dot product, this is what the model is returning. Okay, so it's a lot of movies that I don't recognize, unfortunately. But if you don't recognize a movie, one thing you can do is you can use its genre as a proxy, right? So we should expect at least that if we're looking at a children's movie or an animation movie, the top candidates should contain a few other children or animation movies. And this is not the case. Here it's, we're getting thriller, action, drama. So clearly something is wrong. So hopefully, maybe like according to the cosine similarity, we get something different. And here we're getting, okay, so we're getting the movie itself. So the query movie itself, Aladdin, in the top position. Of course, this should always be expected because if you're asking what is the closest angle between the vector and all candidates, so all candidates will contain Aladdin itself. And the closest, the smallest angle is between the vector and itself. So the angle is 0, and so the cosine is 1. Okay, but it looks like there's also a bunch of other movies that have very high cosine. So, and again here, according to cosine or dot product, both nearest neighbors don't look very relevant to me. So yes, this is not a very good quality model. Okay, so what else can we do? So another thing that you can do is actually visualize the norm of the movie embeddings. As we saw in the lecture, right? So we should expect at least that there's kind of a positive correlation between the number of ratings that the movie gets and the embedding norm of that movie. And this is exactly what we will plot. So here we're generating a scatter plot between, so on the x-axis, it's the number of ratings of a movie, and on the y-axis, it's the norm of its embedding. And then if you hover over one of these points, then it will show you the title of that movie. Okay. So a few, one sanity check that we can do is remember, the top movie that had the highest number of ratings was Star Wars with 500 something ratings, and we do see it here. Okay. So now a couple of things to say about this. I mean, first is we do see this, this positive correlation, at least some trend between the two. But there is a lot of noise, right? So there's a bunch of movies that have very few ratings, perhaps even 0 ratings in the training set, or maybe 1 rating, that have very high embedding norm. So this points to an issue. So why? It's because, for example, according to dot product, these movies that are here will tend to recommended to be recommended in the top, to have very high score because they have very high embedding norm, right? So they even have a higher norm than the most rated movie, which is something a little bit strange. So that's probably why we're seeing a lot of noise in the recommendations here. And actually, if we're lucky, we might be able to recognize, at least for dot product, some of these. Okay, let's see. Some of these titles in the top here, and we do, right? So there's Deadly Cure, Innocence, and so on, which are a bunch of movies I don't know. So now if we dig a little deeper, and we ask why did the model assign high norm embeddings here, it turns out it's because of initialization. So because we're using a very high value for the init standard deviation, so what happens is that some embeddings will end up getting a very high value for the embedding norm. And because they don't have many observations in the training set, we don't visit them very often, right? So we don't get a chance of updating their embedding very often. So it turns out that for those items, the ones that have few observations will stay with a high embedding norm. Okay, and that's why we see this very noisy behavior. So one way to fix this is to be more conservative when you initialize. So we can try initializing with a much lower initial standard deviation, so that at least rare movies will not kind of dominate the predictions of the model. So let's try to do that. Okay, so before, yes, actually, let's just copy some of the code and at least check if changing the initial standard deviation changes this distribution of the norms. Okay, so let's copy this here. Okay, we have the nearest neighbors. All right, so let me just paste the code here. And I'm going to keep in the same embedding dimension and just decrease the initial standard deviation. Let's say to 0.1. Okay, I retrain the model. All right, so now if I try this plot again. Okay, so it looks slightly better to me, but still didn't completely fix the problem. So maybe we need to be more aggressive. So let's use an even smaller initial standard deviation. And actually, this will not completely solve the problem, but let's see how far we can get just by tuning the hyperparameters of the model. Okay. Okay, so not much better, slightly better than what we had in the beginning. I'm just curious, I will do one more attempt where I increase the embedding dimension of the model. Let's see. Okay, so this improved it a little bit more. So now I'm curious, okay, let's generate now the nearest neighbors for the same movie according to this new model. Okay, so according to dot product, which is this top table, so first of all, I think you may recognize some of the top popular movies in the list that we saw. So this is, I think, Indiana Jones movie. Shawshank Redemption is one of the movies that has the most ratings. Titanic, Star Wars. So these are mostly, popular movies. So at least it's a behavior more consistent with what we expect. Right, so that according to dot product, there should be this bias towards more popular movies. So now, according to cosine, okay, so unfortunately, these still don't look good, right? It's still all over the place. So there's action, adventure, sci-fi, there's thriller, crime, etc. So we don't, so maybe we can look a little bit further down the list in case this gets any better. So if we look at, let's say, 12 candidates. Okay, so also for cosine. Okay, so for the first list, it's still mostly popular movies. For the second list, still not very good, right? So I don't see any children or animation movies. You can also try this with other examples if you're curious. All right, so now let's try another fix. Okay, before that, actually, there's one last visualization exercise that we can do. So far, we looked at the embedding norm. We also looked at, some specific examples, some anecdotal examples by looking at the nearest neighbors of certain movies. What you can try to do is kind of get a more global picture of the movie representation that the model learned by plotting all of the movie embeddings. Now, of course, because these embeddings are, in higher dimensional vectors, so they're 10 dimensions in our last model, we need to project them down to a smaller dimension to be able to visualize them. And One way to do this is the so-called UMAP. So think of this as something like PCA, like principal component analysis. So it takes a matrix, and so the difference with PCA is that it will apply a nonlinear transformation from the original space, which is a 10-dimensional space, to the projection space, which is a 2D space. So in PCA, this transformation is linear, right? So we compute a linear transformation that tries to capture the principal components. In UMAP, this is a nonlinear transformation that tries to preserve the pairwise distances. So if two embeddings are close in the original 10-dimensional space, then they should be close in the projection space. Okay. So, okay, let's run this. I think this takes a little bit of time to run. What we're going to do is color each of the movies by its genre, right? And hopefully, what we hope to see is that there is a little bit of clustering, at least, across genres, right? So things that belong to the same genre tend to be close to each other in this embedding space. And yeah, it looks like this is not the case, right? So, and one thing you can do is also, so there's a chart explaining the colors on the right-hand side here. So if you click on one of them, so if you click action, for example, then this will highlight all of the action movies. And it looks like, they're all over the place. So I also like to look at horror, because this in general tends to be pretty tightly clustered, and it's also all over the place. So it doesn't look like the model is learning very much, a lot of relevant signal here, except maybe popularity. So if I look at, let's say, animation and children, then yes. I mean, you could see some clusters maybe around here, but it's not, it's not nearly as good as what we would like. Okay, so with this, so that was our first attempt. Now we're going to look at how we can change this loss function to get to a better quality model. So remember, what we did so far is we just fit the ratings on the observed pairs. So whenever there is an observation, we try to predict that, but we don't care about anything that's not observed. What we will do now is we will add two terms to the loss function. So if you focus on this expression here, what we implemented so far is the first part. Now we're going to add two regularization terms, if you will. The first one is just plain L2 regularization. So this R of UV, we're just going to add the norm of the embedding as a regularization. And then we have the second term, this G of UV. The expression is given here. So this is saying that I want to add to the loss the sum over all users, the sum over all items of the dot product between UI, so the user embedding, and the item embedding squared, right? So what this will do is that for any item and any user, it's trying to push the prediction down towards 0, right? Because if I try to minimize the square of UI.vj, this is the prediction of the model, the dot product. So if I minimize the squared prediction, I'm trying to get the prediction closer to 0, right? And this is why we usually call this term as the gravity term. So it's trying to push all of the predictions of the model down to 0. Another way to think about it is we're putting a prior of 0 on all of the pairs. So everything else, if there is no evidence in the data that the prediction should be high, then the prediction should be as close as possible to 0. And from the lecture, this is the second term in the loss function, if you remember. This is fitting the unobserved part of the matrix, trying to get it close to 0. Okay, so as you can imagine, there will be a tension between these two terms, between the G term, this gravity term, that's trying to push things to 0, and then the observed part of the loss that's trying to push things towards the ground truth for the observed pairs, right? So there will be, now the model will have to sort of do a trade-off between these two terms. Okay. And with these additional terms in the loss, we also introduce additional hyperparameters. So one is for that multiplies this this G term, and this is another hyperparameter that multiplies the L2 regularization. Okay. And now you may recognize these extra parameters. Now our build model function, as before, it takes the ratings data frame, it takes the embedding dimension, the initial standard deviation, but now it takes these extra hyperparameters, the regularization coefficient and the gravity coefficient. Okay. Here, once again, I did some minimal amount of tuning, but I'm sure that you can get better quality if you tune them better. So let's just train the model for now. Okay, so just for fairness, I'm going to, okay, let me stop this training, and I'm going to increase this to 2000. Yes, and another thing I need to change actually is, so remember before in the definition of build model, I commented out the parts about gravity, the regularization part, right? So let me now revisit that and uncomment this. Okay. Okay, so hopefully this should fix it. All right, now if I go back down. Okay, so we're training for the same number of iterations, 2000 iterations. Here I increased the learning rate, so I found that 10 is sort of too slow. And I think that's it. So I'm using similar initial standard deviation. And for now, let's do embedding dimension 10, just to have comparable dimension to the previous model. So now the only difference with the previous one is that we have these extra terms in the loss function. Okay. So here we're showing one extra plot where I'm also showing the different parts of the loss. So the first plot will still be the error on the observations, only measured on the observations. So the second plot is the three components of the loss. So there's the observed loss, there's the regularization loss, and then there's the gravity loss that measures how far you are from zero for all pairs. And then that's the train and test recall as before. Okay, so many things to say about these plots. So first, let's look at the train error and test error. So now the train error is more than 1, so it's almost 1.5. And the test error is 2. So at first glance, this might seem bad, right? So it might look like the quality of the model is actually going down, because before, okay, I don't remember the exact numbers, but I think it was much closer to 1 or maybe even less than 1. But actually, if we at closer inspection, it's this is not surprising because of this extra term in the loss function. As I said, there is this trade-off between the two terms in the loss. So because now the model has to minimize both, has to fit the observations on the ground truth, and also it has to also care about all of the unobserved pairs and have the prediction close to 0 for those. Right. So of course, because now there's a trade-off, the training error itself on the observed part might go up. Okay, so this is not necessarily a bad thing. So another thing to usually that you usually want in these types of problems is that the three components of the loss have comparable values. So you shouldn't have, for example, that one is orders of magnitude larger than the other. So that can be used kind of as a guideline when tuning the hyperparameters. So for example, I'm pretty sure that if I increase, let's say, the gravity coefficient by 100, so multiply this by 100, then probably the scale of the loss function, of the different components of the loss, will be very different. And that's not good. So the last thing is about the recall. You will see that now we lost this kind of behavior where it first goes up and then it goes down. So it seems that it keeps going up. And also the value itself is much higher. So before we were closer to, I think, 2% or 3%. Now we're closer to 10 and 12% on the test and train sets. And again, this is not too surprising because now we have this extra term in the loss that is actually designed to help this kind of metric. So it's helping the model distinguish between the positives and negatives, or the rated versus unrated movies. Okay, so enough looking at the losses. Now we can do the same thing as we did before. We can try to inspect the model a little bit more. And then we can try to tune hyperparameters. This is kind of with minimal tuning. So let's look at the nearest neighbors for the Aladdin movie again. And I called this new model reg model for regularized model. We can look at the old model again as well. So for the regularized model, according to dot product, okay, this is not very different from what we had before. We can recognize here the movies with the most ratings: Star Wars, Indiana Jones, and so on, another Star Wars movie. And now, okay, here it's looking slightly better, I would argue. So at least there's, Beauty and the Beast is another Disney movie. So the genre is animation children musical. So that's pretty relevant, I would say, to Aladdin. Apollo 13 is debatable. So this is an action movie and thriller. Lion King is another Disney movie. So Indiana Jones might be okay. So it's still a little bit mixed. So I'm curious if we go a little bit down the list. Now, if I increase 10. Okay, so it's still a little bit mixed. So I'm sure we can try. Actually, I found in general that increasing the embedding dimension can help. So let me increase this back to 30, and let's see if this is better. Of course, you can spend a lot of time tuning these hyperparameters. It's sort of fun, a fun exercise once you start doing this. So I will not spend too much time because we're almost out of time. I think we have 15 minutes left together, and I'm hoping that we can finish early in case there are some questions. But I encourage you, to revisit this exercise later and play with this model. There are so many things you can add. So as I said, you can generate recommendations for yourself. You can also, try this on other data sets, on the bigger movie lens data sets. You can tune the hyperparameters. You can add features. So really, you could treat this as a sandbox, and you can play with many variations of this model. Okay, so now the model finished training. Let's look at the nearest neighbors again. Okay, so interestingly for this one, even with dot product, it is getting some, I would say, more relevant movies. So Lion King is both popular and relevant. Same thing for Toy Story. Yeah, I think E.T. the Extraterrestrial arguably is a pretty good recommendation. So dot product already looks better. For cosine, we still see Lion King and Beauty and the Beast. Yeah, we see E.T. the Extraterrestrial, Pinocchio, Cinderella. Mrs. Doubtfire is another comedy, I would say also children movie. So this might look better. I mean, at least on this one example. You might look at other ones. So let's, out of curiosity, let's see what happens if we use a popular movie as the query. Okay, so as expected, this should be mostly other popular movies, and it looks like, it gets the other Star Wars movie as the second position. And here too, so it gets Star Wars, it gets Star Trek, which is not bad. Another sci-fi action adventure movie, the other Star Wars movie. So yeah, overall, this looks much better than what we started with. So now one other thing we can do is compare the distribution of the embedding norms between the two models. So this is what we had before after the, the initialization fix. Now with the regularization, it looks much better. So it looks like a much cleaner kind of correlation between the two. And this is what you expect in most models, matrix factorization models at least. Okay, so the last thing we will do is look at the UMAP, the projection of the movie embeddings. I hope that we will see something a little more, some more patterns. Okay, so I think I can already see a little bit more clustering. So it looks like there's, for example, a lot of green over here, a lot of blue over here. Of course, we don't expect to see something that's very clear-cut because the genres by themselves are not enough to explain the co-watch patterns, so things that are watched together or liked together, right? But we can look at a few examples. So action movies, it does look like there are a few clusters. So there's a cluster here. There's another cluster over here. So I always like to look at children and animation. And here I think there are much clearer clusters than we had before. So you can look at some of these here. It looks like some Disney movies over here. Cinderella, Pinocchio, Lion King, Snow White, Sword in the Stone. So these are all Disney movies. Yeah, here are some other perhaps mixed children movies. Let's see if we recognize any patterns. So yeah, the other one is horror. So horror, I think now is a much better clustering of horror movies up here. Maybe another cluster here. Yeah, these look like some pretty popular horror movies, The Shining, The Bird, and so on. What else can we look at? We can look at sci-fi, perhaps. Okay, sci-fi is a little bit all over the place, but you can try to. So it's interesting. Here it gets that it puts all of the Star Trek movies closely clustered together, which is always fun to find these little patterns. Okay, so with that, I think I will stop here. Hopefully this should convince you that at least this latest model is much better than what we started with. You can, again, try many more queries, try extensions of the model, try what happens. I might be curious, for example, how much I can push the embedding dimension up before starting to overfit, right? And how much performance, how much extra performance I can squeeze from the model by increasing the embedding dimension. So with that, I think I'll stop here. Let me take another quick look at the list of questions in case there are some new questions. Okay. So someone asked, how can we get the link of the collab? So sorry I didn't see this question earlier. I hope you got the answer from somewhere else. Actually, you can find this collab online by searching for Google Recommender Systems. This is taken from an open sourced class that I started teaching many years ago at Google. And the collab is linked there, but let me also show the link of the collab one more time before we quit. Okay. So this is the link, bit.ly/rexis-collab. This is actually a simplified version from the collab that's in the recommender systems class, in the open source version of the class. So the class has a much longer collab with more variations and also with a neural network example. So if you're curious about some of these extensions, you can also look at the other version of the collab. Okay, so I think that was the only other question we had. So with that, thank you very much for attending this workshop. I hope you enjoyed it, and I hope you'll continue working on the collab. Continue experimenting with the recommender system. I'm also going to put my email here, walidk@google.com. Feel free to reach out to me if you have follow-up questions, comments. I'd be happy to answer. All right, thank you very much. And I will stop the live stream here. Thanks.